So good morning, everyone. Hope I'm audible to all.
Yes, ma'am.
Yeah, thank you. It's my privilege to welcome you all to the 6-day faculty development program, which is hosted by our Department of Computer Science and Engineering from Sree. First and foremost, I would like to welcome our respected principal, who is always supportive and motivating. Welcome our dear principal, Dr. S.P. Subramanian, sir, to this FTP. And some resource persons have joined us. Baazil sir is there, Madhavan sir is there. So I welcome them. And firstly, I thank them for accepting our invitation, and they were ready to share their expertise with our participants. So thanks to them, and welcome you all to this FTP sessions. And next thing is welcoming the FTP coordinators. They have put a lot of effort in organizing this event. So I welcome Ms. Nishma PS, the coordinator of this FTP, the co-coordinators, Ms. Nilima Mohan and Ms. Aparna V. Welcome them to this FTP sessions ahead. And of course, the participants who are the core of this program. And I hope you all will be getting an enriching session from here. And talking about the motivation behind the FTP that we have chosen, or the theme behind the FTP was, like we all know, the machine learning, artificial intelligence, all these streams were, maybe we were considering it as emerging trends maybe a few years back. But now, if you are an educator, you must know what is artificial intelligence, what is deep learning, data engineering. So everything you must know about all these trends. So it's from that thought we set the theme of FTP as intelligent computing technologies. That is, it will be covering most of the prominent areas which is related to CSE. So I hope this program will be enriching and rewarding for everyone, and everyone will be getting benefited from this. So I once again welcome all the participants over here and all the dignitaries here to the 6-day FTP. Thank you. Thank you.
Thank you, ma'am. It is now my privilege to invite Dr. S.P. Subramanian, Principal, Sree Institute of Management and Technology, to deliver the inaugural address and officially inaugurate this faculty development program.
Thank you. Am I audible?
Yes, sir.
Okay, but my screen is, I'm not able to see my face. I don't know whether it is off from there. Yeah, okay, now it's on. No, so thank you. Good morning, all of you. Respected dignitaries, the head of the Department of Computer Science, Professor Sushma Madam, Dr. Madhavan, resource persons, coordinators of this FDP, and dear participants. I'm extremely happy to be associated with this inaugural session of this 6-day FDP conducted by Department of Computer Science, the topic being intelligent computing technologies. I'm happy also to mention that all the departments in Sree Engineering College is conducting 6 days FTP during this June. This is Department of CSE organizing this event. Already Applied Science and Humanities Department as well as Civil Engineering, both of the departments have completed the FTPs. 2 other FDPs are in progress, organized by Department of Artificial Intelligence and Department of Electronics and Communication Engineering. And the remaining departments, Mechanical and Electrical Engineering, are conducting it during the next week. So it's a good opportunity for the faculty members of Sree Engineering College as well as other participants from outside to get awareness about the various trends happening in the field of engineering and technology. As faculty members, it is a minimum responsibility to get equipped ourselves with the latest trends that is happening, especially in the field of computer science. Maybe about 30 years before, the whole of computer science and engineering, as such, it has come out as a branch, maybe during 1980s or 85s or 90, in that period only. When I was a student, there was no branch like computer science. So the whole development that has taken place is during the last 30 years. So that means in another 30 years, we can't imagine where the department or where the computer science branch is going to end up. So unless the teachers are equipping themselves with every day, unless they are equipping themselves, it will be difficult.
I said that I have not seen a single person here back home. അപ്പൊ എനിക്ക് വിശ്വസിക്കാൻ പറ്റില്ല ഇത് കാണാതെ കാരണം ഇവിടെ ആരും വന്നിട്ടില്ല ജോലി പോയി വന്നിട്ട്. So he said they can't come back because when you lose a job in the Gulf.
Okay, some disturbance in between. I don't know what happened. Anyway, so I'm sure that the 6-day FPP organized by the Department of Computer Science on Intelligent Computing Technologies covers almost all the topics that is relevant to the present day, like artificial intelligence, machine learning, deep learning, biomedical AI, data engineering, cyber security, and things like that. So I personally congratulate the Department of Computer Science, the head of the department, Sree, other coordinators, Nishma, Neelima, Aparna, other faculty members of the departments, and also the participants, especially the resource persons for organizing these events. I formally declare that the 6-day FDP is inaugurated. Once again, congratulations to all of you. Thank you very much. Okay, madam.
Thank you, sir, for your inspiring words and encouragement. We shall now move on to the felicitation session. I respectfully invite Professor Sushma M, IQAC convener, to offer her felicitation remarks. Over to you, ma'am.
Thank you. And good afternoon, everybody. Respected principal, head of the department, Ms. Reshma, and other dignitaries. It is really a pleasure to felicitate all of you for, first of all, organizing this program, felicitate the organizers for organizing this program and the participants who have registered. It shows the passion towards teaching, because teaching is nothing but continuous learning. And we have to update ourselves, and Department of CSE has Department of CSE has delivered on its promise of keeping themselves abreast of the technology. So I congratulate the CSE department and also wish the participants a very happy learning. Thank you.
Thank you, ma'am. As we come to the end of the inaugural session, I would like to invite Ms. Nishma, FDP coordinator, to deliver the vote of thanks.
Good afternoon, everyone. It's my privilege to propose the vote of thanks on this auspicious occasion. First and foremost, I express my sincere gratitude to our respected principal, Dr. S.P. Subramanian, for inaugurating this FTP and for sharing his valuable thoughts, encouragement, and best wishes with all of us. His inspiring words have set the perfect tone for the days ahead. I would like to express my heartfelt thanks to Professor Sushma M. for her thoughtful felicitation and motivating words that inspired us all. I extend our heartfelt thanks to all the distinguished resource persons who have graciously accepted our invitation to share their expertise and enrich this program with their knowledge and experience. We are truly grateful for your willingness to be a part of this academic endeavor. I would also like to thank all the participants from various institutions for their overwhelming response and enthusiastic presence. Your commitment to continuous learning and professional development is highly appreciated, and we hope this FTP proves to be a meaningful and enriching experience for each one of you. My sincere appreciation goes to the management, the organizing committee members, and all my faculty colleagues whose dedication, teamwork, and unwavering support have made this program possible. A very special note of thanks to Ms. Shrishma, HOD, Department of Computer Science and Engineering. From the initial planning stages to the final execution, her unwavering support, motivation, and leadership have been instrumental in making this FTP possible. Thank you, Miss, for believing in the team and guiding us every step of the way. Finally, I extend my heartfelt gratitude to everyone who has directly or indirectly supported the Department of Computer Science and Engineering in organizing this faculty development program. With these words, I conclude my vote of thanks. Let us actively participate, interact, and make the most of the sessions planned over the coming days. Thank you all once again, and I wish everyone a wonderful, insightful, and enriching FTP experience.
Thank you, ma'am. With this, we conclude the inaugural session of the 6-day faculty development program on intelligent computing technologies. We shall now move on to the technical session of the day. It is my pleasure to introduce our resource person, Dr. Baazil P. Thampy, Assistant Professor in the Department of Computer Science and Engineering at Sree Narayana Gurukulam College of Engineering, Ernakulam. He has over 11 years of combined teaching and research experience and has made significant contribution in the areas of machine learning, signal processing, image processing, IoT, and AI/ML applications. Today's session is titled Introduction to Machine Learning from Concepts to Practice. We are delighted to have him with us today and eagerly look forward to his valuable insight. I now invite Dr. Baazil P. Thampy to take over the session.
Good afternoon, all. Thank you, ma'am, for the warm introduction. I extend my gratitude to the principal, head of the department, and organizers for inviting me to this event. Let's jump into the session. So I will share my screen. Okay. So is the screen visible? And am I visible?
Yes, sir.
Yes.
Okay, thank you. So this is a basic introduction into machine learning. Don't expect too much. So this is a basic fundamental session. So here we will learn concepts in quick, and then we will practice with the help of programming. Okay. So here we are using Python programming for this session. So what exactly is machine learning? As you all know, it's a field of study that gives computer its ability to learn without being explicitly programmed. So learning without being explicitly programmed. So machine learning is basically a subset of AI. Then we have deep learning, which is the advanced subset of machine learning. So in this session, we'll be covering only the machine learning aspects. Okay. So here in machine learning, you will have data, then we have the machine learning algorithms, and based upon that, we'll be making predictions. The traditional programming approach, we usually give the inputs and the programmer explicitly write the rules, and based upon the rules, the program execute and the output is produced. Whereas in machine learning, we are actually giving the input data as well as the expected output. And based on the input to output relationship, the ML algorithm learns it and will produces the output as the trained model. The different types of machine learning. The common types of machine learning are supervised learning, unsupervised learning, reinforcement learning. In supervised learning, the input along with the input data we are feeding, we'll be giving labels for training that data. So basically we use this supervised learning for the task of classification, regression kind of applications. Whereas in unsupervised learning, we will just give the data as such without any labels. And the ML algorithm or the deep learning algorithm will find the hidden patterns in this data. And commonly we use this kind of unsupervised learning in applications such as clustering, dimensionality reduction, etc. Then we have the reinforcement learning. where the agent learns through rewards and penalties. It's a kind of trial and error application. We use this reinforcement learning in self-driving car kind of development, gaming, robotics also, all we use reinforcement learning. Now, there is one more classification which we commonly heard. It is semi-supervised learning. It's partially supervised and partially unsupervised. Now, when you look at the machine learning pipeline, so this is a basic pipeline of machine learning pipeline where it starts from data collection. Then we clean the data or we'll pre-process the data. Then we apply feature engineering techniques. Then the model is trained. Once the model is trained, we evaluate the model to check how good this model is. And if the model is found satisfactory or performing well, then we will deploy it in our applications, real-world applications. So let's see each of these stages in detail. So data collection. So where will we get data? Lot of databases are available. Then we can get data from sensors, IoT kind of devices. Then through APIs, we can get data. Sometimes data may be given in the format of CSV file or JSON file kind of things. So data is all around us. Okay. Then this data we collected has to be processed before we giving into the ML model. So the quality of the collected data, if the quality of the collected data is good, then definitely the model is going to perform well. Now, let's see how a data is loaded. Let's share my Colab page. Okay. So first step is data collection, right? So here we are importing packages necessary for processing the data. So here I'm using two libraries. One is Pandas, another is NumPy. So we import the libraries first. Now I'm creating a sample data set. So sometimes we will be giving data directly. Sometimes we'll be reading this data from CSV files. So here, what I'm trying to do is that I'm creating a data, then writing it to a CSV file, then fetch the data from CSV file for the machine learning application. So here, I'm creating a data, sample data with student IDs and name. The fields are student ID, name, age, department, and marks. Now using Panda data frame, I am converting this data into a data frame. So this is how the data looks like. You have the student ID, you have the name, age, department, and marks. Now I'm just writing. So before writing, I can show you that here there are no files in the Colab directory right now. Now, when I run this code, so here I'm saving the CSV file. Okay, I'm saving the data frame as a CSV file first. Then I'm reading that same CSV file for further processing. So normally in practical application, you will have a data set, and here I'm assuming that the data is in CSV format. Then we just have to load that CSV file. But in this case, since there is no CSV file, I'm creating a CSV file using the data I have created here. Right. Now the file is saved and the file is loaded, and when the loaded data is printed, you can see the same data appearing here. Now, when you go and check the files, here you can see that a new CSV file is created, right? So df data frame to CSV, using that function, you will be saving the data into the CSV. Then using Panda frame PD, pandas, we read that CSV file, read CSV function. Using that, we are loading that data and the load data is being displayed. So this is how we load a data into our ML model. Now, let me continue with the presentation. So we have collected the data, we have loaded the data. Now we have to do the cleaning operation. The data that we have collected may have many impurities. So if you feed the ML model with these impurities, the model performance will not be as you expect. So we have to clean the data first. So what are the common kind of issues that appear in data? Some issues like range violations. Suppose the GPA should not be greater than 4 and you are having values more than 4, then sometimes there will be duplicate rows. Now there will be inconsistencies in categories. Some people may enter as New York, some people may write it as New York City. Now there will be mixed unit kind of errors will be there. Some people may write the temperature in Celsius, some will be writing it in Fahrenheit. Right? Now, some cases there will be missing data as well. So how to deal with these? We can't give the data with missing data, or if the data is not uniform, if the data constraints are violated, if inconsistencies in categories are there, then we can't give the data as such into a ML model. So we have to do the cleaning process. Let's clean some data. Yeah. So data cleaning. Here we will be seeing how the missing values are handled, duplicates are removed, data type corrections are performed, how the outliers are detected, and finally preparing the clean data for our ML model to be trained. So here also we are using the same libraries, import pandas as PD and NumPy. These are the two popular libraries which are used to handle the data in ML and DL applications. So we have imported the libraries. Then, as previous explained, I have created a data. I have created a data set with fields student ID, name, age, department, and marks. And this data is converted into data frame for efficient handling. So using pandas data frame function, I'm converting this data into data frame structure. Now, here you can see the data being loaded. And here in this given data set, so whenever you get a data set, you have to explore, or you have to go through the data and find what all issues are there in your data set. Now, when you examine this data set, you can see that for many, in some fields, you can see NaN. It's not a number, right? So in fields here, in the on the second index, you can see the age is NaN. And on the fifth index, you can see the marks as NaN. Now, also you can see that the name Meera is appearing twice, right? The row number 3 and 4, these are duplicates. So in this particular data set, also you can see that, see, on the age column, the value is given as 200. The value age is given as 200. You can, that's not going to happen, right? So age 200, the average lifespan is somewhere around 60 to 70. So in that case, a current age of person reaching 200, it's an outlier, right? So you have to search through the data and found the outliers and find what exact issues are there with your data. So in this data, which we have created, we have a duplication issue, we have a not a number issue, then we have constraint violation issues as well, right? So we have to perform the data inspection. We can do the data inspection. I didn't run this data, that's why we have that error. Okay. Now, let me, so in data frame, there are 3 different functions. One is head, then info, and describe. So we can go use these functions for data inspection. So when you call that df stands for data frame, okay, df.head, then what will the function does is that it will list us the top 5 rows. Okay, the top 5 values will be listed like this. Okay, now when you call df.info, it will list what are the features of the data types. What are the data types? Here you have the column, the number column is there. Then we have the student IDs. Student ID is there, name is there, age is there, department is there, mark is there. So what kind of data types are there? So it will be displayed. Then when you call the describe of function, it will give a description of your data set. It will give you how many items are there, what is the mean value of a particular field, what is the standard deviation, what is the minimum value, what is the maximum value, and what is the 25%, 50% value, 70% of the value. All these information you can get. So by closely inspecting the data, find out what issues are there in your data. Then first we are going to handle the missing value issue, right? So here I'm using the function fill NA, right? Here I'm using the function fill NA. So here in the age field, we have a non-zero value, not a number value is there. Then for mark also we have a missing value case is there. So we are trying to replace those 2 values with the median value. Some people replace it with mean value. Some people replace it with median value. Generally, we use median for replacement because it's less susceptible to the outliers. So here what we are trying to do is that take the data set. On the data set, wherever the fields are not a number, okay, fill the not a number with the median value of that particular column. And what in place is equal to 2 does is that it will replace this on the actual data set. We don't want to do it on a different data set. On the same data set, on the same data frame we have collected, we want to replace these values. So here see, for John it is NAN and for Arun mark is NAN. Now by doing this, see, the John's age is replaced with the median value. The John's age is replaced with median value and the Arun's mark is replaced with the median value of mark. So this is how we handle missing values. So if that field is very important, we have to keep that instance. Otherwise, if you have sufficient amount of data, then discarding that field also work. But if you want to keep that instance, in that case, we can't feed these missing values into the machine learning model. Instead, we have to replace it. Now, removing the duplicate data. See, after replacing the not a number case, still we have the issue with index 3 and 4. The instance 3, label 3 and 4, it's the same data. It's the duplicate data only, right? So here we are using the function. So these functions are there within the data frame. Pandas data frame provides you these functions. So you just have to call it. It is drop duplicate off. by calling drop duplicate off, what it does is that the data frame will search the database or the data set and find out which all instances are duplicate instances, and it will remove those instances. Now, after removing the data, the resultant data is stored on the original data frame itself only, right? So we are running this. So you can see before duplication removal, before you remove the duplicates, there were 7 instances. Now, after removing the duplicates, we have only 6 instances. So the shape defines, there are 2 parameters for shape. One is the row number and second one is the column number. The first index represents the row number, which also represents the index number. Sorry, index number. And then we have the instance number, and then we have the column number, which refers to the number of fields. 1, 2, 3, 4, 5 fields are there. Now, if you want to display the data frame, just call df. See, now the row labeled with 4 is gone. The 104 Mira, the instance, only one instance is there. Duplicate instance has been removed. Now, handling the inconsistencies. Now, in this data, you have observed that here for CSE, they have used upper cases. Here for CSE, they have used lower cases. So such kind of issues comes. What happens is that the model will, if you give it to a machine learning model, it will take CSE capital letters as one department and small letter CSE as another department, right? So this should not happen. It should be uniform. To handle the inconsistent values, we can use several functions. Here we have used, so whatever is the department, okay, whatever is the data in the department, we are converting that into upper cases by using the function str, string.upper of. Calling that function, we are converting all the department names into upper cases. So here we can see small cases are there, for mechanical small cases are there. But when you run this, the output shows all the departments in capital letters, upper cases only. Okay. So we have handled the inconsistency issues as well. Now we have to do the outlier detection. As in our data set, we observed that with Arun, the age is an outlier. Age given is an outlier. Even though it's a valid value, but it's an outlier value, right? We have to identify such values and we have to remove the outliers before feeding it to the ML model to get a good predictive model. So here, what I have used is that there are different outlier detection mechanisms are there. Here we use interquartile range method, right? By using IQR, we will find which are all are the outliers. So using 25% quantile and 75% quantile, we will find the lower bound and upper bound for the data set. So any value lower than the data set, the threshold that we have identified will be an outlier, and any value upper than this value, greater than this value will also be an outlier. So we are identifying the outliers. So by using, if the age after the lower and upper is computed using IQR, we will check whether the age given is lower than this or age is greater than this. Then definitely this is going to be an outlier. So by running this, we can find out which all values or which all instances in the given data set are outliers. Here we are focusing on the field age only. See, the age of Arun is identified as an outlier. So there is an outlier is there in our data set. We have to remove it. So to remove this, we can write a simple Python code. It's data on the data frame, which all on the field on the column age, if the value is greater than or equal to lower and less than or equal to upper, then that is a valid data. It is not an outlier. So keep those values only. Remove all the rest of the values. That's what we have written over here. This is a basic Python script only. Now, if you run this code, you can see that as the Arun, the instance of Arun is an outlier, we have dropped that particular instance. Finally, we have a clean data set for model to be trained. Okay, so we have identified what all outliers are there, what all data inconsistencies are there. We have removed all those and we have made a clean data set. Now this can be further processed into for the next pipeline stage of the machine learning. Okay, I hope this is clear. Finally, at the end of the session, we will do a hands-on. Okay, this is for a detailed explanation only. I have made these separate slides. We will be doing a hands-on at the final part where we will be writing the code line by line on Google Colab. Okay. Now, so the data cleaning is over. Now let us move on to the next pipeline stage, which is feature engineering. Feature engineering. So why feature engineering is very important? First point, it is very important because it will improve the accuracy of the proposed model. So well-crafted features, okay, if the features are well-crafted, then the hidden patterns in your raw data can easily be identified by your ML model. Now it reduces the complexity. If your data has more insignificant features or irrelevant features, then keeping them make the learning task complex for a model. So if you remove such irrelevant features, then it simplifies the learning task. Now it enables better patterns. The algorithms that are used in machine learning, the models usually generalize based on the given data. So to get a more generalized version or an effective generalized version, the input should be meaningful. So the quality of the data collected, based on the quality of the data collected, then by applying feature engineering, we can improve the accuracy, we can reduce the complexity, and we can do better pattern analysis. Now, what are the techniques that we use in feature engineering? The feature engineering can be subdivided into feature selection, feature creation, feature transformation. In feature selection, what we will do is that from the list of available features, we will choose the most informative features and we'll discard all the noise features. That means all the irrelevant, redundant features. We are talking about the columns. The features means the columns, right? Now we will remove all the unnecessary columns. In the previous phase during data cleaning, what we have removed actually, we have actually removed the instances, the rows we have removed, or we have tried to resolve issues with the rows. Now we are going to with the columns. We are focusing on the columns. Which all columns are needed? Which all are relevant? We keep only those features. Suppose in the given case, if you are going to predict the mark of a student, the student name has the field student ID or student name has nothing to do with a mark, right? So those features such as student ID and student name are not relevant. If you feed the ML model with this ID and the name, then it is very complex for the model to learn. And the model will not be able to generalize well as well. So the feature selection, through feature selection, we are actually reducing the dimensionality And this task that we are performing will help us to prevent the overfitting issue. We will see the overfitting issue later. Then next technique is feature creation. So in feature creation, we are actually creating new meaningful data from the existing data. So we are deriving new data from the existing data, provided the model get a richer context for learning. Okay. Then we have the feature transformation. Many machine learning models performs better with data in a specific range or distribution. And sometimes it will be more easier for the model if the scales are comparable. If the features are in different scales, then it is very difficult for the model to learn. But if the models are on a given scale, then it will be easier for the model to find which all are outliers and all. So feature transformation. So feature engineering can be divided into these three techniques. Can be done using these three techniques. Now, let's see how feature engineering is done. Okay. So here we will be seeing how the features are selected, how features are created, how features are transformed, how encoding can be done, feature scaling as well. So here we will be seeing all these things. Here also, we have imported the basic libraries, pandas and numpy for handling data. Now, from here on, we are using a special library called sklearn. sklearn stands for scikit-learn. It's a wonderful library for performing ML tasks. So in sklearn, since this is feature engineering is part of pre-processing, so I am importing the necessary libraries, which are label encoders, one-hot encoders, and standard scalars. So here we are importing the necessary libraries for performing feature engineering. So here we have a sample data set. Now in this data set, we have removed all the outliers, everything. The data cleaning has been done. Then only we will be moving on with the feature engineering part. Let's do with the feature selection. So in this sample data set, as I have already mentioned, the student ID and student name has nothing to do with the prediction of marks, right? So I can easily remove these two fields, or these two features can be removed before feeding into the ML training. So feature selection, so remove student ID and name because they do not contribute to our predictions, right? So the selected features are, so from the data frame, which consists of all these fields, all the features, I'm selecting only 4 features, which is age, department, mark 1 and mark 2. Mark for one subject and mark for second subject. So rest of the fields I'm discarding. So skip or discard all the irrelevant features. So now you have a new data frame selected features which consist only of the relevant features of the data set. So I'm displaying it. One second, let me run this program. Otherwise it will be an issue. Sessions. 1 second. Now we'll connect. So I hope you are familiar with the Google Colab interface. If not, towards the end of the session, when we are doing the hands-on, you can ask queries. I will go through that as well. Okay, now it is connected. Let's run this. Okay, the libraries are imported. The initial data is given. Then we are selecting only this. Now, the data being fed into the ML model will have only these fields. Which are features? The age feature all field, department, mark 1 and mark 2. All the irrelevant features or field has been removed. Then we have the feature creation. So, create new meaningful features from existing features. In feature creation, we are actually deriving new data from the existing data. And if we do this only if that data, the derived data, provide richer context for our ML task. So here I'm creating a new field called total marks. Okay, I'm creating a field called total marks. How that marks is being created? By adding the features, the values in mark 1 and mark 2. So for each student, I am computing the total marks and I am updating the total mark field on the data, same data frame. DF is our original data frame. On that data frame, I am appending the total marks. Now you can see the total marks for each student is being displayed. So for understanding purpose only, here I have used the original data frame. If you have used the selected data frame, only here the total will be added, right? These are two different variables, data frame variables. One is selected features. This is DF is our original only. So in the original only, I have added this. Okay. Now we have calculated, we have created a new feature called total marks. Then let's do some transformations as well. Right? So the transform features to improve learning. So here I have created a percentage field. Okay. So that means the mark, based on the marks, I have created a new a feature called as percentage. Okay. Basically, this is also can be considered as a data creation, feature creation aspect. Now we will go the aspect of categorical features. Now here in your the department, right? It is being labeled as CSE, ECE, EEE, etc. Now, if I want to label them, because for a model, machine learning model, these are nothing but some values, right? So instead of keeping this, it's at CSE, ECE strings. Instead of keeping this as strings, why won't we make it more simpler as a symbol data labels, such as 0 for CSE. So whenever CSE comes, make it 0. So whenever ECE comes, make it 1. Whenever EEE comes, make it 2. Right? To do that, we can use label encoders. We can use label encoders. So for label encoders, we use the function label encoder of. The label encoder function is being imported from sklearn preprocessing package. Okay, we have that encoder function. Now we are calling that encoder to fit and transform the field department. We want to transform. The department is there. Currently it is in string format. We wanted to convert into a number format or a numeric format for labeling purpose, right? So we call this function encoder.fit transform of the features inside department. Now, whatever result is being returned, you add it into the original data frame as a new feature data or department label. We will be adding it as a new feature called department label. Right? So on the original data frame, using transformation, we have transformed the department into department label, and we have added that also into our data frame. Another is one-hot encoding. sometimes we want to represent the categories on a binary format. In binary format, we have to represent categories. So to do that, using the panda frame, we use the function get dummies of. Okay, inside pandas, there is a function get dummies of. So what this function does is that it will check on the column on the feature department, and it identifies that there are how many departments are there? 1 second. Here we have CSE is there, ECE is there, EEE is there, right? So we have 3 departments. Now what this does is that it will create 1 second. Sorry. So by one-hot encoding, we are converting this into a binary format. Here you can see department CSE, department ECE, and department EEE. Now for Anu belongs to CSE department. So for CSE, the value is true. For rest, it is false. For true, it is 1, and for false, it is 0, right? Here the values are represented as Boolean only. So we can use this for one-hot encoding. Because when the labels are being fed into the model, the ML model can perform well if proper one-hot encoding kind of category classifications are being done. So here the CSE, Rahul belongs to ECE departments. For ECE, it is true. For rest of the department, it is false, right? So during feature transformations, whatever transformations are needed for the feature, we will perform. So if you want one-hot encoding, we want to include one-hot encoding, then you can call this function and you can include one-hot encoding. Then the transformation feature scaling kind of transformations. See, here we are taking 4 features: age, mark 1, mark 2, and total marks. Now, age will range from 0 to 100, right? Normal range can be set as 0 to 100. Then mark may range from 0 to, sometimes the exam is on 50, all right? So 0 to 50. Assume that another subject is on the range of 0 to 100. Now, when you compute the total marks, these two, mark 1 and mark 2, they are on different scales. We want to bring them on a same scale for analysis, right? So for that case, we can use standard scalars. Different scalars options are there. One option is standard scalar. So we can call the function standard scalar. The function standard scalar is there within the sklearn preprocessing. In the sklearn preprocessing, we have the standard scalar, right? Now, when you call this standard scalar, right, the function is called, an object is created, and object dot scalar dot fit transform of function. We are asking to fit the features with the standard scalar. Which features? The features we have selected, right? Now, the features that we have selected is appended as a new scaled data frame, right? It is stored on a new data frame variable. Now, when you display it, you can see that instead of age 0 to 100, it has been converted to another range, right? The range of -1 to 1, or 0 to 1, or 0 to a given range, right? Likewise, using whatever the scalar that you are using, depending upon the scalar function that you are using, that will be mapped to that will be scaled to a different range. And instead of keeping the values as such, these kind of values, scaled values, will be easier for the ML model to get trained, because the such models works well on distributions, uniform kind of, the general distribution kind of thing, data. So marks are being here converted, scaled, and being applied. Now here we have used only the scalar, the standard scalar. There are different other scalars. Another one commonly used scalar is the min-max scalar. It will convert the values in the range of 0 to 1. Okay. Then we have the absolute scalar. Absolute scalar will convert your data, the features, into the range of -1 to 1. Even though these range values will be difficult for us to understand, but for a machine learning model, it will be easier for understanding, right? For us, by hearing the age 20, it makes sense, right? But seeing the value 0.58, it doesn't make any sense. But for the model, it is sufficient. For an ML model, this is sufficient. Okay. Now we have done the feature engineering, right? We have done the feature engineering. Now let's move on to the next phase. The data split. So after feature engineering, you have a pre-processed data, which is perfectly suitable for an ML model to get trained. But we are not giving the all data, we are not giving the data as a whole into the ML model for training. Instead, we are splitting this data into 3 sets: the training set, validation set, and the test set. Using the training set, we train the model. Using validation test, we verify and we will do the hyperparameter tuning. Once everything is okay, then we will deploy it on the test set, which is the final evaluation. So let's see how the data is being splitted. Okay. So here in this Python notebook, we'll be doing the data split. We want to split the data into train, validation, and test. So for that, we are importing the necessary libraries. These libraries are all is there in all the previous slides. But here for data splitting, we are using a specialized function which is there in the scikit-learn.model selection. So inside scikit-learn.model selection, for selecting a model, in that we have a function called train test split. So we are importing that function, right? So the libraries are imported. Now we just have the data. Okay. We have the data. So here we have used the data age, experience, salary. So 3 fields are there. Even though I just gave the values here only. The pre-processing, everything has to be done. Okay, once everything is done, I'm assuming that everything is done. Then we are taking this data. Okay, I'm trying to apply a supervised. I'm going to showcase a supervised learning aspect. So I'm saying that which all are the inputs and which is the output, right? We have to show which is the label and which are the features. So here, based on age and experience, my model is going to predict the salary. That's what I'm trying to do. Assume a situation like this, right? Based on age and experience, our model wants to predict the salary. So what we will do, we will set the features as the input variable or the features as age and experience. That is the input features. And what is your output feature or the output variable? It is the salary. So I'm setting the input features and output features. Okay. Input features and output features. By using x dot head of, it will by default, it will print top 5 values, right? So the top 5 values are age and experience in X, and salary. Top 5 values in salary field are this. Now, we wanted to do the splitting. There are different types of split. Commonly used splitting ratios are 80-20 or 70-30. Some people may go with 90-10, right? But commonly, generally used, the split ratios are 80-20 or 70-30, right? So here, using the train test split function, I'm giving my input features and my output features, and I'm mentioning what should be my test size. Suppose I want 20%, you should give the test size as 0.2, right? If it is 100%, you should give it as 1. If it is 0%, you should give it as 0, right? So 0 to 100 is mapped to 0 to 1. That's it. So the test size I'm mentioning here. So I want 20% for testing. So what all is remaining, it will be used for training only, right? Here we are not mentioning, explicitly mentioning the training size. We just need to mention the test size only. So what all are left over, it will be used for training. So 80%. By writing this, it is clear that the 80% is being reserved for training and 20% is reserved for testing. Now, one more field that we commonly use is random state is equal to some number. Here we have used the number which normally we see in many of the codes. It is 42. You can write any number, 12, 10, any number it will work, right? So what is the purpose of this random state? In CNN, we use the terminology random seed. What is the purpose of that? Every time when you do this and you evaluate a model, right? Suppose I take 10, say 100 instances for training. Okay. Assume that there is 120 data. I used 80 data for training and 20 for testing. Now, when I try with model 1, okay, model 1, assume that this is a machine learning model, support SVM model is there. I used SVM and I trained on this 80 instances. 1 to 80 numbers are used for training and 81 to 100 is used for testing, right? Next time, when I try with another model, assume that linear regression model is being used. Okay. Now there, if I select 1 to 20 for testing and 21 to 100 for training. And when I get the output for both models, suppose accuracy, let's keep the simple terminology, accuracy value. One model SVM gives accuracy 92. Model 2 with linear regression gives us accuracy value 85. How can we compare them? Because these two models are trained on different data items, right? Not the same data item. So every time when you split the data to get the same sequence of training, same instances for training, ensuring that and same instances for testing is being used, we use this random state. Okay. So random state is used for ensuring that every time when you run this code, the same set of, even though it is randomly selected, the samples are randomly selected, the same instances of samples are being selected. So when you call this function, what is the result you get? You will get you will get 4 values. The first value will be the features for training. Second value will be features for testing. Third value will be the output value for training. And fourth value will be output value for testing. So let us run this code. So of the 16 instances, here we had actually 16 instances, right? Of the 16 instances, 12 is used for training and 4 is used for testing, right? But in our case, we mentioned about validation split as well. So how this validation split can be done, right? So let us take another case. Here we are using 70% for training, validation 15% and testing. So we are talking about all these implementation using the scikit-learn package, right? in CNN kind of implementation using other packages, there are different functions are there. But in scikit-learn, how we can do this kind of splitting, right? To do that, we have calling the train split function. First, we will call whatever is there for validation and testing, we will combine them. So 15 plus 15, 30%, right? So first we will split the data into train and a temporary data for that combines validation and testing, right? So I will set it as 30%, 15 plus 15, 30%. Now I get the training features, which is 70%, and remaining 30% I keep it an temporary variable. Now I again split that temporary data set or temporary variable data into 50-50. So whatever is 30% of that 30%, 15%, half is for validation, half is for testing. So I will take that temporary. See, here we gave the input as the actual input features X and Y. But here for splitting, we are giving it as X temp and Y temp. Now we apply the test size, we set the test size as 50%. Here also we are setting the random state as 40, right? So random state setting is very important for comparing models. Okay, to compare different models performance and to ensure that the input is not depending on the data. So to do all the testing evaluation things, definitely the random state has to be set. Now let's see. If you run this code, the training will be 11. For validation, it is 2. And for testing, it is 3. Why, sir? Because it is 15 and 15. Why this difference? Because the number that we have given, it is not perfectly divisible. That's all. That is the reason. Because if you give 11 for training, based on the 70-30, 11 for training and remaining 5 for testing of the total instances, whenever you divide this 5, it can't be, validation cannot be 2.5 and testing cannot be 2.5 or 3.5. It has to be an integer value. So here for validation, we have selected 2 and the remaining 3 has been selected for testing, right? Now, when you receive these values, we use for X val, X test, Y val, Y test. Okay, so whenever we call train test split of function, it will return 4 values, 1 for validation features, okay, validation input feature, validation output feature, test set input feature, test set output feature. Okay, so we learned how to split our data according to our requirements, right? So once data splitting is done, we can move on to the next phase. Data splitting is over, then we are moving on to the, okay, one slide is missing over here. We will do the data training here itself. Okay, we'll see how the models can be trained. Okay. So once splitting everything is done, now we have different machine learning algorithms for different tasks. So based upon your task, you select, based upon your task and the type of data, we will select the models and we will evaluate the models, and whichever model gives the best result, we will go on with that model, right? So now let's see how the model training can be done using different machine learning algorithms, right? So here what I'm doing, I am importing pandas, numpy, as we have already seen. Now see, here I have used a data set called iris data set. Iris data set is a benchmark data set. It is been widely used data set, right? Whenever models are being new ML model or deep learning models are being introduced, if it is classification kind of classification kind of task, definitely we will go with the iris data set to test its performance, right? So we have the iris data set. Now this iris data set is there within the sklearn library. Okay, you don't have to download it separately. There, for learning purpose, scikit-learn has provided some by default inbuilt. There are some data sets of which I am using the iris dataset. If this dataset is not there, by using the load function, you can load the dataset. Now, we have to do the train test splitting that we have seen. We have to do the pre-processing. Then here, there are different machine learning algorithms in this notebook, Jupyter notebook, IPython notebook. Okay, we'll be using logistic regression, decision tree classifiers, random forest, K nearest neighbor classifier, and SVC classifier, support vector machine classifier. Right? So these ML models or ML algorithms are there inside the scikit-learn library. So logistic regression is there in the sklearn.linear model package. Then decision tree classifier is there in sklearn.tree package. Then random forest classifier is there inside sklearn.ensemble package. Then K nearest neighbor, K neighbors classifier is there inside sklearn neighbors package. And SVC is there inside sklearn support vector machine class package, right? So we will import those packages and the libraries. Then for evaluation purpose, which model performs well, right? So here we are using a basic metric for evaluation, that is the accuracy score. Okay, we are just using the accuracy score. Where can we get this function to compute accuracy? It is there inside sklearn.metrics. Okay. Let me So till this part, we have, this is just the basics of machine learning only. Many of you may know these topics. If you are a beginner, you haven't had any kind of ML kind of experience, then only this session will be fruitful for us, for you. Otherwise, it's just a revision for you guys. Now, in the upcoming sessions, I was told that more advanced topics will be covered. Okay, so since this is the first session, we'll be seeing only the basic introduction. Okay, it's connected. Now let's run. If the running is proper, then definitely you can see a tick mark here and the numbering will come here, right? Okay. Now we have imported the libraries, then the data set is loaded. So since this is an inbuilt data set, we can use the function load iris of the data set will be loaded into the variable iris. Now we are converting this iris data set into a data frame, right? And in the data frame, we are specifying which is the output variable. There are features inside iris, of which one feature is target. The target feature has to be given as our output prediction variable, right? So features and the target classes are defined, right? So this is basically the loading of the data set and identifying which all are the input features and which all are the output features. Now we split the data. Here we are using 80-20 rule. Using train test split, we have splitted the data. So whatever necessary transformation or feature engineering are needed, you apply this. So I'm applying scalar fitting. Standard scalar is being applied. Now, training a model, right? So how will you train a model? So I have a logistic regression. I am calling logistic regression. Okay, my first model is logistic regression. I'm setting how many iterations has to this go, because for every model, there will be some input parameters, right? So for logistic regression, the input parameter is you have to mention how many iterations has to be performed, okay, inside the model. So I'm setting a logistic regression model with 200 iterations, 200 training iterations. Now I'm saving the model name, okay? Now I'm calling the fit of function. To train a model, we use dot fit of function, okay? The model name dot fit of. Now, as input to training, what we will give? What we will give? We will give it as the training input. Okay, input features will be given. The output features will also be given. Okay, so here I am giving X-train. Okay, since feature engineering is done, I am using X-train scaled and Y-train is being given for fitting the model. So what happens is that based on the given input features and output features, the logistic regression model will run 200 iterations and the model will fit, right? Once the model is fit, we will use it for prediction. Okay, how good its predictions are, right? So when to predict, we will call the trained model, because we are training this model, we will be using the same name, LR model dot predict of. Using predict function, we will call this model, and inside we will give the test parameters, input as test parameters only. For prediction, we have to give only the test parameters, input parameters only. Whereas for training, you have to give both input training features and output labels as well, right? Right. Then we give that. Then we are just printing the accuracy score based on the prediction result. Okay, we have the white test where actual values are there. Then we have the LR prediction where what was the prediction for each test set by the logistic regression model. Let's run this. And now we have got a value 1.0. 1 indicates 100% accuracy. So for iris data set with 200 iterations, the model perfectly fitted, right? Now, let's do the same with a decision tree model. Okay, so one model is logistic regression. We have seen how it is being trained. Here, when you invoke the logistic regression for the first time, you have to mention how many iterations it has to run. Okay, now even if you don't give that, it will run on the default value. Right? You can explicitly give, or by default value, the default value will be taken if not given. Now, decision tree, here we are calling the decision tree classifier function. In decision tree, we have to mention the random state value. Okay, for training, we have to mention the random state value. Now, this function, based on that, a decision tree classifier object is created, a model is created, and on that model, we are applying same fitting function. Here I am giving the training inputs and the output training labels. Okay, when you call model.fit_of, model name.fit_of, what happens? The model training happens. In ML model, since the number of instances in all the iris kind of data sets is very less compared to other large data sets, okay, the training will happen instantaneously, right? But for deep learning models, this training will take some time and you can see the progress of that training. But here with just one click, the training happens. Okay. Now, to test your data, you will have to call the function .predictOf and give the input as xtest. That you give the input test parameters for testing the model. Now, what will be the result? The predictions will be the result. Now, you compare the predictions with the actual labels. Here we are comparing your predictions with the actual labels and we are calculating the accuracy value. So, decision tree, yeah, the model is trained. Right, so now we have trained the logistic regression. We have done the decision tree. So what I'm trying to show is that, see, the model can be used easily, right? It's just one, instead of using decision tree classifier of, we just call what logistic regression of. That's it, right? So whichever model you call, to train it, we use the same function .fit_of. And for testing, we use the function .predictOf. This is how the model training and testing is done. Once the model is trained, we will test it with our test data set. Okay. So these are another examples of decision tree classifier. Okay. So this is decision tree classifier we have seen. Now we have the random forest model, just called the random forest of function. Now here I have explicitly mentioned that the estimators, 100 as estimators. Definitely, this is not it is not like the random forest have just two input parameters. Definitely, it may have more than two parameters as well. even if you are not giving the parameters explicitly, it will work on the default values. Okay. Now, random forest model dot fit of is being called. The prediction is being called. The values are being printed. Similarly, for KNN, just call the K nearest neighbor classifier function. Just mention how many neighbors, nearest neighbors you are expecting, right? And based upon that, you set that parameter. Then you call the fit of function. You call the predictor function. Likewise, you can train and test any ML model. For SVM, this is another famous model. So just call SVC of, right? Then the model dot fit of and model dot predict of will work. Okay. Then after training, we will compare the results of these predictions, and whichever model gives us better results, we will go with that model. Okay. So this is how we train different ML models by using the corresponding functions for that model. Okay, we have these model algorithms within the library package of sklearn, right? Choose these different ML models and train your data set, and whichever model gives you better accuracy after evaluation, careful evaluation, so if that model works for unobserved data or unseen data, then go ahead with that data set. Okay. Then let's move on. Once the model is trained and tested, what are the evaluations that we can do? Okay, what are the different evaluations metrics that we have? Let's see that. Okay, so there are once the model is trained, we have to evaluate how good that model is, and definitely the evaluation metrics help us to find out which model performs better, right? So for different tasks, the metrics may be different. For classification, we have confusion metrics, accuracy, precision, recall, F1 score is there. Then for regression kind of task, we have the R square, mean absolute error, mean squared error method metrics are there. Then for segmentation, we have dice coefficient, then intersection over union kind of metrics are there. So for different tasks, different standard metrics are there. Okay, we just have to use those metrics and we have to evaluate how good our model is. So one of the commonly used model is the evaluation metrics in classification is the confusion metrics. So in confusion metrics, you have actual positive class is there, actual negative class is there, predicted positive class is there, predicted negative class is there. Now, this TP and TN are our, if our actual case and the predictions are a match, it will comes as TP and TN, right? Suppose, let me explain it with the help of a real world example. Assume that as cat and dog classification. Okay. So here it will be actual cat, actual dog, predicted cat, predicted dog. Now, if my model predicted it as cat, okay, model predicted it as cat, and actually it is a cat, then it comes here as a true positive case because my prediction is correct, right? Similarly here also, if the prediction is dog and the actual case is also dog, then that's a correct prediction, right? So these two are correct predictions and these two are incorrect predictions, right? What does this mean? Because the model predicted it as cat, but actually it was a dog. Here, the model predicted it as dog, but actually it was a cat. This is how we understand the confusion metrics. So higher the values in this diagonal, okay, the principal diagonal elements values are high, and keeping the other values, other cell values as 0 as possible or near to 0, then that indicates that your model is performing well. Now we have different key metrics, accuracy. So all the computations of accuracy, precision, recall, everything is based on these values, TP, FN, FP, TN, right? So accuracy is the total accuracy, overall correctness will be measured, but this metric is not reliable when your data has imbalance issues. Okay, assume that you have 1,000 cases of a patient tested for COVID cases, and of which of the 1,000 cases, only 100 cases are what? only let's make it more smaller value, make the imbalance the bigger issue. Let's assume that the COVID positive cases are only 10 cases out of 1,000. Only 10 cases are COVID positive. Rest of the cases are COVID negative. Now, when I develop a model, okay, when I develop a model, and if I model says, okay, if even though the model is not working for any input, my model says it as COVID negative, then the accuracy value, when you test the accuracy value will be above 90%. Okay, the accuracy value will be above 90%. But whatever input you give, the model will just say it as COVID negative, because most of the cases the results are COVID negative only. But that model learning is not good, right? The accuracy cannot measure, will not give a pure evaluation metric whenever there is class imbalance problem. If the class balance is there, then definitely you can go ahead with the accuracy values. Now, the other metrics are precisions. Okay, so precision measures of the all positive predicted, how many were corrected. Okay, so your model predicted cat, of which how many were actually cat. That is the precision measurement. And recall is the, or in other words, it is also known as sensitivity. It measures on the actual positive. Out of the actual cat, how many were actually predicted as cat. Okay, so one is precision, one is recall. Now, instead of using these two parameters, there is a harmonic mean of these two parameters as computed, and F1 score is being, another metric known as F1 score is also being used. Instead of using separately precision and recall, F1 score indicates a clear harmony between the precision and recall. Okay, it takes both precision and recall to compute the F1 score. Then we have the AUC ROC curve, area under curve region of curve. For regression metrics, we have these are just the commonly used metrics only I have mentioned here. Its mean absolute error is there. Just compute how much the value deviates from the original mean absolute error, and we will take the average of that. Now, mean squared error, for every difference you take the square and you take average of that. And if the square root of mean square error is taken, you will get the root mean squared error. Right. Now, let's see how the evaluation is being done. Okay. Model evaluation. Okay, for model evaluation, I am maybe explaining cross validation also. So let me show you that on the slides. So model evaluation, regression metrics evaluation, mean absolute error, mean square error, and root mean square error. Now, what are the analysis that we can learn from this? Okay, so there are two main terminologies. One is bias and variance. Okay, if a model has high bias, it means the model is underfitted. If a model has high variance, it means the model is overfitted. Okay, so we want a perfect trade-off between these two. Okay, so if your model is a very simple model, then that model will not be efficient to capture or will not be efficient to make future predictions based on the training data, because your model is very simple, right? It can't handle complex features. The model is not complex, right? It is a simple model. The understanding of that model is beyond its capability, right? So in that case, underfitting happens. Underfitting is also known by the term high bias. Okay. Now, in case of high variance, you are making the model too complex. Instead of having a decent model, you are making the model too complex such that your model will work well for training data, but when you test it for the unseen data, the error will be very high. Okay, so in underfitting case, during training itself, you can see the error value will be very high. When you train the model, you are getting accuracy 30%, 20%. That means for training, you are getting those values, then indicate that there is high bias is there. The model is underfitted. Why? Your model is not good. So improve the quality of the model or make model bit more complex. Okay. Now, when you go with overfitting, when you have a complex model, you train the model. Then for training, during training, when you observe, the errors are very small. For example, for training data set, the values are showing us accuracy is 99.5%. But when you test the accuracy on the test set, you are getting the accuracy values are 75, 60 or 50. Lesser values you are getting. Then that clearly indicates that your model suffers from overfitting problem. Okay. So we wanted a model in between. We want a trade-off between these two parameters, bias and variance. So we wanted low training error. Okay. We wanted to reduce the test error as minimal as possible. Then we wanted a model, a good model with which has good generalization capability. So definitely this model will be bit more complex than this simplified model, but less complex than the this very complex model, right? So the trade-off should be there. We need a balanced model. We need a balance between underfitting and overfitting. Now, to ensure the model works just for a particular sequence of data, it's not working for other cases. What we do is that, okay, we perform an operation called k-fold cross-validation. Okay, k-fold cross-validation is being used. Here, what we will do is that we will divide the data set into different folds. On the first fold, okay, assume like this. You have 100 data, okay, 1 to 20 is this, 21 to 40 is this, 40 to 60, 41 to 60 is this, 61 to 80 is this, 81 to 100 is this. Okay, I'm dividing my data into 5 data set into 5 chunks. Of this chunks, I will reserve the first chunk for testing in my fold 1, and I will use remaining 4 chunks for training my model. On the next fold, I will reserve the second chunk for testing and will use all the remaining 4 chunks for testing, for training. On the next fold, I'm using the third chunk for testing as test data set and remaining as chunks as training data set. Similarly, we create multiple folds. They generally used for k value for cross-validation is 5. Some people also use 10-fold cross-validation as well. In that case, there will be 10 folds. 10 such folds will be there, of which a particular portion will be reserved for testing in one fold, and a different will be reserved on the next fold for testing. Right? Now, for each fold, we will compute the errors. For this, we will compute the error. What was the testing accuracy? For this, what was the error? For this, what was the error? For this, what was the error? For fold 5, what was the testing error? Now, you take the average of these errors, then you will get the cross-validation error. Okay, so before initially we choose a particular random seed and we splitted the data set. And we have used only that data set on that particular selection of instances for training and testing only. We have checked whether the model is working fine or not. But other combinations are not being taken. So using k-fold validation, we ensure that other combinations are also taken and testing and training is done. And for whenever, even though the instances that we take for training is not affecting our model. Okay. So if you say that my model is performing well, it should be independent of the instances that you are taking from the data set for training and testing. Okay. Let me explain that with another example. Assume that in one test, okay, when you take 1 to 20 for testing and remaining 21 to 100 for training, your model gave 90% accuracy. Assume that your machine learning model, okay, a linear logistic regression model give you 90% accuracy. But when you take 21 to 40 for us testing and remaining for training, then in that case, suppose your model performance gives you 60%, then that clearly indicates that your model is not good. Why? Because when from the data set, the instances which I choose for training and testing affects the model, right? So the model is not able to generalize perfectly. So that is not a good model. So the cross-validation error also helps us to find out which model is better. But now let's move on to the coding part. So we have model evaluation. Yeah. So we have the pandas, NumPy, the iris dataset is used, splitting is done. Now, along with the test split, I have imported another package, which is cross validation score. This is another function, right? This function is there within model selection. Then rest of the things are there. Now, from the metric part, since this is a classification problem, okay, I have used the confusion matrix, F1 score, recall, precision, accuracy score. So these functions are being imported. Where are these functions residing? It is there inside sklearn.metricof. So all the necessary libraries are being imported. Yeah. Now the data is loaded. So just call head of, it will display the top 5 values. Okay. Now we call the X-train split. Then we do the feature scaling, everything. Okay. And model is fitted. Okay. The predictions results are achieved. And based on the predictions, we will compute accuracy, precision, recall, F1 score, everything. Okay. See? So the accuracy is 100%, precision is 100%. So out of predicted, all were correctly predicted. Of the actual cases, all the actual cases were predicted. Then the F1 score is there. Then you have the confusion matrix. So the confusion matrix here stands for 3 classes. So there are class 1, class 2, class 3 is there. Because in iris dataset, there are 3 different types of species are there, right? So class 1, class 2, class 3, class 1, class 2, class 3. So 10, 10. See, the diagonal elements are 10, 9, 11. The principal diagonal elements are 10, 9, 11. Rest of these matrices are values in the cells are 0. That indicates that our model performed well for the test set. Okay. So we can get these measures. Now, let me show you the cross validation. How to do the cross validation. So for doing cross validation, I am calling the function cross val score of. Okay. So for cross validation, here I am using logistic regression. I'm using the ML model as logistic regression. Then the data is given, input data features are given, output labels are given. Then I am setting the value for K. In the K fold parameter, you have to specify what is the value for cross validation. Here I'm giving the K value as 5. So cross validation is set as 5. And I want to measure the accuracy. Okay, for each iteration or for each fold, I want to compute the accuracy. So these accuracy values will be printed. I am also printing the mean accuracy value as well. Once I get the accuracy scores, I am computing the mean accuracy score. That's what I'm doing over here. So see, here you have 5 accuracy values. The first accuracy value is 96% or 0.96. Both are same. This is 100%. This is 93%. This is 96% and 1%. So 100%. So you have 5 different accuracy values, right? So the best accuracy you got for this model was 100% and the least accuracy was 93%. So the average accuracy value is 97.3 will be the average accuracy. So there is, as see in our previous example, when we run, we got 100% accuracy. Based on that, we can't say on a single run, on a single fold, you can't say that your model is the best model. Okay, we have to do the evaluation, cross validation also to make to ensure that this is not just a magic that has happened because of the instances that you have selected for training and testing. It is independent of those instances. Okay. Now, if I have multiple models, okay, using a for loop, I can call these models one by one, and I can apply, and I can find out cross-validation on all those models as well. This is not needed for the time being. Okay. So this is how we compute cross-validation. So based on the cross-validation, we ensures that, okay, the model will work even if you choose on a real deployment, you choose a different sequence of instances, definitely this is going to work. Now, let us move on to the final portion of our presentation. So validation is done. Then we are discussing about the ensemble methods. Okay. Sometimes one model, using just one model for prediction may not be sufficient in practical deployment scenarios. Suppose you have a logistic regression based classification, then you have SVM classifier. Sometimes one for some types of input, your model 1 performs well, but for another type of inputs, your model 2 performs well. Now, there are in your actual deployment, these two cases type of instances may occur. So in that situation, maybe we can combine this model 1 and model 2 to give an ensemble model. So ensemble model is nothing but combining standalone models such that you are improving the accuracy or the efficiency of the model, right? So these ensemble approaches can be divided into three, broadly divided into three: bagging, boosting, and stacking. In bagging, okay, you will train n models on random data subset in parallel. Okay, that means you have a data set. Okay, you have a data set. You will divide that data set into sub data sets. You have the data set, you divide that data set into sub data set. Now take one subset and train model 1. Take set 2 and train model 2. Take set 3 and train model 3. Likewise, you take the model, okay, and train it on different subsets of the same data set. Okay. Now, when we deploy, what we will do is that, what is the output predicted by the model 1? Model 1 says class 1. What about model 2? Model says class 2. Model 3 says class 1. So then we will go with the majority opinion, right? There are different approaches are there, but for make it simple, I can say that we will go with the majority opinion. So since the two models trained on the subset of the data set has predicted it as class 1, we assume that the actual class will be class 1 only. The model prediction will be class 1 only. Likewise, so this is a bagging is such application. Here, n models are trained on the subset of the actual data set, right? Then comes boosting. Here, the models are trained sequentially. Each model, okay, one model is trained, then whatever mistakes are being made by that model, it will be, the second model will focus on the mistakes done by the first model. So XGBoost, AdaBoost are the commonly used boosting ensemble methods. Then we have the stacking. Here we will be using heterogeneous machine learning models. Okay, we will train on diverse models. Then we combine their result using another learner. Maybe it will be a logistic regression learner or a linear regression model learner. Okay, we combine the results and we will make the final predictions. So we have three different ways of ensembling or combining the models. One is bagging, then another is boosting, and the last one is stacking. So in this XGBoost and AdaBoost are widely used. Also the random forest. Random forest is actually a collection of trees, right? So a collection of different decision trees forms the random forest. So this is also widely used. Then, so now we have loaded the data. We have done the data cleaning. Then we have done the feature extraction, feature engineering. then we have splitted the model and trained the model, then we have evaluated the model, right? Let's see the whole process on a single program. Okay. So this is the entire pipeline. Okay. Here we'll be seeing the complete machine learning pipeline. So for that, if you can access computers right now, you can open the Google Colab. How many of you can access Colab, or you have any doubts in how Google Colab is being used? Please type it on the chat, because this is just the hands-on experience. I'm just trying to share the hands-on experience. I don't know whether you are sitting, you accessing the session using mobile phones or laptops. If you have access to system, definitely you can try this. Okay, this is the entire summary or the complete pipeline of whatever we have discussed in our presentation. Will you be able to do the hands-on right now? You can write in the chat. You can type on the chat. I'm just looking at the chat. So can we do the hands-on now? Participants, please respond. Okay. Got just one response. What about the others? Fine. So we will do the hands-on, right? Okay. So if you have doubts on Colab, I don't know the different diversity of the participants. Okay, how diverse you are, I don't know. If you are a beginner or you don't know Colab at all, then I have to start with how to open a Colab like that. Otherwise, I can just start with the programming. So anyone who doesn't know what is a Google Colab, just put a question mark, Colab with a question mark on the chat. If you don't know nothing about Google Colab, just put Colab with a question mark. Okay. So Rajni ma'am says, what is a Colab, right? Fine. Thank you. So to do the programming, to train a ML model, we need a platform or an IDE, right? So normally for doing the Python programming all, we use the Anaconda version. Okay, we use the Anaconda IDE. I can show you those things. What is an Anaconda? Anaconda IDE. Okay, so normally for Python programming, we used to install this Anaconda IDE. It's an open source distribution. You can just download and you can use it for works for Linux, Windows, everything operating system. But there you have to install this, and inside there are different softwares are there. Inside that IDE, you have the Spider notebook is there. Some people will be using Jupyter notebook is there, right? Different softwares are there for programming, for the IDE for programming using Python. We have different softwares inside that, inside this package, right? Now, if you don't have a system, because sometimes when you do the Python programming, especially the deep learning kind of programs, it is very complex, and you may need, since the amount of data is high for deep learning kind of application, needed is very high for deep learning kind of applications, we will be needing GPU-based systems, right? Suppose you don't have a GPU-based system, how will you do the programming? Then in that case, Google has provided provided us with a platform known as Google Colab. You can just search for Google Colab on Google. So colab.research.google.com, right? So here you have to sign in because I have already connected. This is being appearing on my screen. Otherwise, a window will come. You can just sign in into Google Colab with a valid Gmail ID. That's sufficient. Now, there are different plans for Google Colab. The basic free version gives us sufficient support. But if you want advanced computational computations are needed, in that case, you have to go for the premium versions of Google Colab, right? So this is an IDE. It acts like an IDE similar to the Anaconda Jupyter notebook, where you can do coding everything online. You can store the code in your Google Drive as well. So whenever you are traveling, you want to get the code and run it, then you can do it from anywhere, right? So that is the package. Now, when you, if you have signed into Google Colab, then normally what we will do is that we will click on open, we will click on new notebook in Drive. Okay, click on file, new notebook for Drive. Okay. Now, here, this is the cell. Okay, this is the cell where you can write your program or you can write your comments. Okay, if you want to add a code cell, okay, if you want to do the programming coding, okay, then you have to add a code cell. Now, if you want to write some comments for explanation purposes, you have to do something. Then the non-executable files you can add as a text cell. Okay, so file. Okay, on Google Colab, we have taken file, new notebook. There, to add more cells, you can just put code cell, you can put plus code, or for adding text cell, you can just put. You can navigate the cells as well. Okay. 1 second. I accidentally clicked the running button. Okay. Now, if you want to, so this is a text cell. This is a non-executable cell. This is a text cell. Hi, my first program. Right? So this is just a text. It is non-executable. I want to make this, move this cell upward. Then you can, by clicking this arrow, you can move this up. If you want to move this cell down, by clicking this down arrow button, you can move this. Right? Now here, the first thing that you have to do is that we have to import our packages. Right? We have to import our packages. So which are the packages? Import pandas. Okay, here we are importing pandas. Then model selection, train test split function is there. Scalar is there. We are using linear regression model for training. Then we are metrics, because we are applying a regression. We are trying to do a regression problem. We are taking the regression metrics. And for saving the model, I have used import pickle. Okay, I will explain about import pickle later. Now, fine. So you can also try with this code, import pandas as PD. So since the time is less, I will copy this code into your chat. You can paste it and you can try it. At the end of the session, I will share all the programs and presentation slides as well. Okay, but just to get a hands-on experience, it will be, if you can access the machines and you can try this code, that will be really helpful for our session. Okay, so we have imported the packages. Just type it. Then run it. For running, this is the button. There is a play button kind of button will appear here. Whenever you type code and you just click it, it will run. And here it will show how many second time it took to run this code. Right? If you are using an complex application where GPU is needed, by default, this will not be running on GPU. It will be using the basic capacity of the Colab hardware. So if you want to use the GPU, then you can go to runtime there you can select change runtime type. By default, it will be CPU. If you want GPU, you can select GPU. Okay. So whenever you are changing the runtime environment, the connection get reconnected. You have to reconnect. Okay. So now whatever code that we are running is now running on the Colab GPU, not the CPU. But for machine learning these kind of simple codes, GPU is not needed. Okay. For advanced CNN unit kind of applications, definitely GPU is needed. When you are dealing with image kind of data set or the NLP kind of data sets, right? So there definitely you need GPU, right? Now, the next part, create a sample data. Okay, so here I'm creating a sample data. This is for house price prediction only. Okay, so what are the fields? Area is there, bedroom is there, age of the house is there, and based on that, price per square feet is given. Okay, so 1,000 square feet bedroom house with the 2 bedrooms with the 20 years old building. The price is 30 per square feet, right? So this is just to showcase a house price reduction, because previous example that we have shown is the classification. Now we are seeing the regression kind of application. So if time is less, I will run here itself. Okay, I'm not just copy pasting. I will just give the I will copy the code into the chat box as well. So you can try this one. So here we are creating a data set. Okay. So with some sample values, area is given, bedroom is given, feature age is given, and the prediction or the output label, price is the prediction or the target. Okay. So a data set is created. The time is almost approaching our 2 o'clock. Okay. I'm just giving the code assets. You can try. You don't have to type it. Okay. The topic is vast. We are just seeing the basics only. Okay. What is the pipeline? How it has to be done. Then pre-processing. So in pre-processing, here I'm just applying the transformations. Okay, the values are in different ranges. I'm bringing that into using a standard scaler. The standard scaler, see, in Google Colab, whenever you point your mouse pointer above the function, it will show the description. Okay, so which function is being used? X minus mu by S, where X is your data, minus mu is the mean, by standard deviation. Using this formula, the scaling is done. Okay, in standard scaler, using this formula, mathematical formula, the scaling is done. So you can do the scaling. Okay, I'm just giving some time for you to copy paste this code and try it on Google Colab. So we have imported the packages. Then we have, since we don't have a data set, we have created a data set and we have applied feature engineering. In data pre-processing, that includes data cleaning and feature engineering. We have just used only feature engineering part only, transformation only. Okay. Have you completed the, up to this point? You can give a thumbs up in the chat box. If some errors are popping up, you can mention about that. Then I will be able to resolve that issues. Up to this over. Can you type on the chat? Have you tried this? Okay, is it working? Okay, fine. Yes, thank you. Now we are going ahead with the training and testing splitting. Okay. training and test split. Here on the scale data, okay, on the scale data input parameters, this is what we have discussed, the output labels and the test size is mentioned and the random set is set, and based on that I am splitting the data into training and testing. Now we can try this. So our feature engineered data set is being splitted into two. Okay, thank you, Renjuma, for the feedback. And thank you others for responding. Thank you so much. Because since this is an online session, I can't see your faces, whether you are accessing using mobile or laptop. That's I don't know that. Okay. Now let's do the, so after splitting, what is the task? We have to do the training, right? So here we are using linear regression because our task is not classification. We want to find the exact amount. What is the price? It is not like cat or dog, right? It is like 20.5, 30, 40. So any number, right? Any value will be the price for the house, right? So to do that, we are using linear regression and I'm calling. So here I'm setting this to the object called model. Then I'm calling model.fit of the training data. So using dot fit of, the model is trained on input features along with the output feature. Okay. The model training is done. Okay. By your model training, whether the model training is, you're getting message as training is completed or not. Now, once the model training is completed, now we have to evaluate that model. For evaluation, we have the test set, right? So using test set, we'll call model dot predict of. Okay. Hey model, predict using this test set. So what are your predictions? That will be stored on prediction variable. And based on the predictions and the actual results, we will compare how the model is working. Right. So here, since this is a regression problem, we are using mean absolute error. One second, training is showing a screen. Okay, training completed. Thank you, thank you. Thank you, Rajni. It's great to see that you are working early. Thank you. So we do the model evaluation. We will get mean absolute error, mean square error, and R square. These error values, mean absolute error or mean square error, we want, the objective is to minimize these two values. Okay. When I can say that model is good, if the mean absolute error and mean square error are low values, if it is near to 0, that means model is good. And for R square, the value has to be high, right? It should be as high as the maximum value is 1 only, right? So if the value is nearing 1, then that is a good case. Okay. So mean absolute error, mean square error, R square values we can print. One second. Okay. Yes. Switching a controls in simulating. One second, I'm not able to copy paste the code. You can check your prediction scores as well. Okay. So now we understood that, okay, since the R square value is high, and it is almost near to 1. And the absolute errors, even though it's 4 and 18, it's a decent value, because for regression kind of things, the values will be it will not be in the range of 0 to 1. It will be a real number value only. Okay, so this is a reasonable value only, and the amount of data we have used here is very less. For that reason, accuracy may be compromised. The model may not be able to learn properly. Usually we go for machine learning models whenever the amount of data is less. If you have larger data, definitely you can go with the deep learning models, but deep learning models are complex, whereas machine learning models are comparatively simpler models. Okay, the complexity is less for machine learning models. Now, you found that your model is good, right? You wanted to save this model for future use. Once you trained everything, training everything takes more time, right? Once you train the model, you suppose definitely for deep learning models, it is sometimes it may take 2 days, 3 days of time for training, right? But here it happened instantaneously. Now I want to save this model for all future use. For future predictions, I want to use this model. How I can use that? That is the deployment part. So here, for this deployment only, for saving the model only, we have imported the package pickle or the library pickle. See, we have imported the library pickle. Why this pickle? I wanted to store the trained model for my future use. Maybe I will not be using this model right now. After 5 days or 10 days, I want to test on a new instance of data. How I can do that? Okay, that's a deployment part, right? So to save this, what we will do, we will open a file, okay, with the name model.pkl. This is just the file name only. You can save it in any file name, but the extension should be pkl for pickle package, right? So model.pkl1, or we can say that since this is an fdp.pkl1, right? Comma, in write mode, you are opening that file, okay? And into that, you are dumping the model. This name should be exactly same as the model being trained. So here I have trained on model MODEL. The name, everything has to be, it is case sensitive. It has to be exactly matching. So here the same model is being dumped using the pickle package into the model.pkl file. Okay. When I run this code, you can see that in our files, the files are listed over here. In our files, a new file is created with the name model.pkl. Okay. Now you can copy this file into any machine, and on that machine, just run the below code for testing a new instance. That's it. You can deploy the trained model on any other machine. You don't have to retrain the model. Retrain the model only if you find that the model is not performing well for your real practical implementation. Otherwise, you don't have to retrain the model. This is a trained model. Okay. Now I will share this code. Okay, it's almost time. I know. Just give me a couple of minutes. Okay, I will wind up. Okay, we can also save the model. Now, just to showcase that, sir, I have saved the model. Now, I didn't give any input and test my model. It was all like the data instance we have given initially. It was divided into training and testing. What if I want to test it for a new instance, right? So in that case, what we have to do, we have to load this model. Okay, the model will be copied to some other machines. We have to load that model, and to that model, we have to give a new instance and ask, based on this input, what will be the price? What will be the prediction? Okay, to do that, we can use this code. See, with open of a model. So we have to write in read mode. Here we are using the read mode only. Okay, we have to open the trained model in read mode. In any other machines you are copying this model pickle, you have to run this code, right? You have to open that. Then using the pickle library, pickle load off. Okay, using that you have to load the model. Now on the loaded model, you have this model. Okay, the trained model is here available inside this load model. Now what we can do, we can give a new data.
Okay, this is a new data. I'm creating a data frame. It explicitly I'm mentioning area is 22,000 because it's 2,200. In this data, there is no 2,200 is there, right? 2,200 is not there. Some values below 2,000 up to 1,000 is there, and above maximum value is 3,000, right? Some values are there, and based on that, I'm saying that my area is 2,200. There are 4 bedrooms. The age of my building is 7. Okay. Now, when whatever transformations you are applied on the actual data has to be applied on the new data as well, because on the initial data set we have performed some kind of translation. So some scalar fitting we have done, right? Standard scalar we have applied. So on the new input data also the same transformation has to be done. Never give the inputs because your model is trained on ranges of in age. Assume that this is area, right? So it is trained on ranges from -1 to 1 with values 1 minus 1.40, 0.7, 1.4. And for bedrooms, the values corresponding trained values were -1.3, -0.3, something like that. Now, suddenly you give the input values as for 2,200, the model doesn't know, right? So we have to convert this 2,200 into its equivalent format so that we will call the transform function. So we will transform the new data into the ML range, ML model trained range. Then we will call the model.predictor function. Okay, call the model.predictor. Same as here, since I have loaded the model as new model only, I have write it as load model of. Normally we call it as model.predictor. This is the variable name I have given for the loaded data set, loaded trained model. Sorry. Now, inside I am giving the scaled new input and I'm calling for the prediction, just printing the prediction. So it's printing as 75.2. Okay, now if I change this value to 1,800, okay, there are 3 bedrooms. What is the house is 17 years of old. What will be the average price? Just run this. It will say the predicted price is 50.41. Okay. So this is how we test our model or we deploy our model for future instances prediction. Okay. So this is the entire pipeline: data collection, pre-processing, training, evaluation, and final deployment. So now it's time for one second. It's the last slides. Okay, so there is deep learning model. Then the advanced deep learning models you will be seeing in the upcoming sessions of this FDP. The advanced version of machine learning. Actually, the advanced machine learning is nothing, is the deep learning, right? It's an advanced subset of the machine learning. Now there you will be using convolutional neural network for image recognition, object detection. For image object detection, definitely CNN kind of networks are good. If you are working on time series data, speech recognition kind of thing, then LSTM kind of models are there. For NLP based LLM, especially for LLM kind of models, you can use transformer models. Then for generative models, for Gen AI, you can use GAN kind of networks. So basically, there we extract the features automatically. Here we have to manually extract the features. So that's a basic difference between machine learning and deep learning. Even though deep learning is a subset of machine learning, where they differentiate. But how can you differentiate them? In machine learning, it is a duty of or the responsibility of the programmer to explicitly extract the features, okay, or extract the data or do the cleaning, everything. You can't give the data as such. You have to do several cleaning, pre-processing, everything. Then you have to do the feature extraction on your own. And once everything is done, then the model will learn will learn on the pre-processed everything data. Okay, but for this kind of it can automatically for deep learning models from images, CNN can efficiently extract features from images. But for machine learning models, it can't directly take features. We have to say which method is used to extract features. What kind of features has to be extracted? We have to explicitly program. That is the basic difference between classical ML and deep learning. Okay. Now the final slide, the questions and discussion. Now you have any questions, you can put it on the chat. So that's for. Okay. Now, you have any questions you can ask? Now, since the time is over, I will share you my mail ID. So if you can have any queries, you can drop me a mail. You can connect with me at baazilp@gmail.com. You will also share my Okay, I have a question. Definitely, I will ask that question. 1 second. Let me share my contact number. Okay, fine. So since bagging trains multiple models in parallel, does it needs more computational power? Yeah, definitely it needs more computational power than a single model. Okay, since it's an ensemble model, the complexity will be high compared to the normal models. Okay, normal single model. But when we compare for machine learning ensemble models, when you compare it with the deep learning model, okay, I will put this in another way aspect. Suppose you have a problem, okay, you can solve it with using an ensemble machine learning model, or equivalently you can solve it with a deep learning model. Okay, in that case, which model you should go? Definitely you can go with the ensemble machine learning model because it is far less complex than the deep learning version. But definitely when you take the normal machine learning model, say logistic regression and an ensemble model, definitely the ensemble model takes more time. If you say a normal decision tree and a random forest, definitely random forest will take more time for training. Okay, so computational power will be slightly high, but our machines won't show that difference. The difference will come up only if you are applying deep learning kind of application, CNN image kind of data set. If you are inputting large amount of data set, the volume, veracity, everything is right. In that case, definitely it matters. The capacity of the machines matters. Otherwise, for machine learning models, we can easily implement. But if you can solve a task using machine learning, go with machine learning. Only if you are facing issues, the evaluation source that there is scope of improvement, then only go for deep learning models. Okay. And deep learning models are good when you have little time for feature extraction, everything. Any more queries? I hope your queries answered. Okay, thank you.
Thank you, sir, for the informative and engaging session. Your insight into machine learning and its practical application have provided valuable learning opportunities for all participants. With this, we conclude the forenoon session of day 1. We sincerely thank you, sir, for the excellent session and all participants for their active involvement. We request all participants to stay on and continue their enthusiastic participation.
Thank you all. Thank you all.
Now we are moving on to the afternoon session of day 1 of 6-day faculty development program on intelligent computing technologies, organized by Department of CSE, CMAT. We are delighted to continue our learning journey with another insightful technical session. It is now my privilege to introduce our esteemed resource person for the afternoon session, Dr. Sumit K. Mandal, Assistant Professor in the Department of Computer Science and Automation at the Indian Institute of Science, Bangalore. Dr. Sumit is actively involved in teaching and research in advanced areas of computer science and has contributed significantly to the field through his academic and research endeavors. Today's session is titled Basics of Large Language Models and System Optimization. On behalf of the Department of Computer Science and Engineering, I extend warm welcome Dr. Sumit K. Mandal and invite him to take over the session. Over to you, sir.
Thank you for the nice introduction. I hope I'm audible. Can one of you please confirm?
Yes, sir.
Okay, and my screen is visible, right?
Yes.
Okay, thank you. Just a moment. Chat open. Okay. So, very good afternoon, everyone, and yeah, thanks for introducing. It's my pleasure to attend and give a talk here. So yeah, I mean, without further ado, I'll just start myself. Myself, Sumit. I'll start with a brief introduction of myself. So I obtained a dual degree, which is a BTech plus MTech in BCE from IIT Kharagpur back in 2015. Then I was in Synopsys for 2 years till 2017. After that, I went for PhD. Initially, I joined Arizona State University. Eventually, I graduated from University of Wisconsin-Madison in 2022. After that, I joined as an assistant professor at IISc in 2022. So that's about myself. And yeah, I mean, we're all colleagues. You don't need to call me sir. You can just call me Sumit. So sorry, I mean, there is some mistake. I'll just see this today, not next day. Okay. So what will we see or what will we learn today? We will first learn about basics of large language models, and then we will discuss about some acceleration technique of large language model. When we say acceleration technique, I mean like how to make the models run faster. And then if time permits, we'll also talk about or discuss on something called speculative decoding, right? One important thing, please ask a lot of questions. Okay, I don't have many slides, or even I don't mind if we just discuss 2 or even 1 out of these 3 topics, but ask questions. Even if you have some stupid questions, or if you think the question is stupid, please go ahead and ask. Okay, with that, let me, before going into large language model, let me first try to give you the context. So why these large language models are important. There are many sequence to sequence tasks, which is typically used in natural language processing domain. So for an example, I hope every one of you use Amazon, right? So whenever you, let's say, bought something in Amazon, if you're not happy, you go back and then you want to complain, so you immediately hit the chat box, right? So you probably wrote a long description of whatever is your complaint, and then the reply you will get is thank you for your question, or thank you for staying with us, right? So there is no human being who actually replied or who actually posted that initial answer, right? So it is chatbot, or those replies generated automatically, correct? Now you can say that, okay, I mean, maybe the reply is same all the time, but when we have a model, like when we have a chatbot, then depending on your query, the reply might be different, right? And that's the task of this, or that's the example of sequence to sequence task. So yeah, chatbot is one example. Then there is machine language translation. If you go to unknown place, if you are not able to understand the language, then usually we go to translate.google.com and then try to see like what we should talk, like how we should talk with the locals, right? That's the machine language translation. And believe me, there is no lookup table. There is no table which says that, okay, if this is the question, then this should be the answer in another language. Or if this is the sentence in one language, this should be the answer in another language. There is no table. So it's a model. There is a model. So that's machine language translation task. Text summarization, which is being heavily used by our students today. Let's say there is an assignment where they have to summarize a research paper. What they do, instead of going over the research paper, they just go and just upload the paper in, let's say, ChatGPT, Gemini, some tool, and then it nicely summarizes the text, right? So in all these contexts, or in all these tasks, both the input and output are a sequence of words, nothing more than that, right? So the input is sequence of word. The sequence can be small or large depending on the task. For an example, the sequence for text summarization task, the input sequence for text summarization task can be very large. Input for machine language translation might not be that large, right? Now, there are several machine learning algorithms for sequence to sequence tasks. Most importantly, there is recurrent neural network, which was there and which was used commercially for a very long time. Then recently transformer algorithms and then transformer with multi-head attentions came into the picture, which actually changed the entire game of this natural language processing. And today you take any of the model like Gemini, Copilot, ChatGPT, DeepSeek, any of these models use this transformer with multi-head attentions. So today we will see what is this transformer with multi-head attentions. But before that, let me quickly tell you what is this recurrent neural network. Again, recurrent neural network was used for a long time for these natural language processing tasks, but they have some drawback. I will also tell you what's the drawback. Before that, let's see what's a recurrent neural network. So this recurrent neural network is an algorithm where a sequence of input is mapped to a sequence of output. Again, it's a sequence to sequence task, or it is performing a sequence to sequence task, right? Now, this particular figure is actually showing one example of recurrent neural network algorithm where you can see that there are multiple of these input which are denoted by X, and then there are outputs, right, Y. So let's see how these outputs are generated. So again, X1, X2, X3, you can imagine that they are nothing but words. Some representation of words, we will see how to represent a word or token, but for now, you can just think that they are nothing but words. So yeah, I mean, whenever we have this RNN algorithm, then this RNN algorithm takes this X1 as input and then some initial state as another input. This can be a dummy state for the first word. Okay, and then this RNN algorithm provides this Y1 as output. Now, whenever we say RNN algorithm, you can think that it's a machine learning algorithm. It has bunch of equations like multiply and accumulation. Some computation is happening inside. Now, whenever it is producing this Y1 as the first output, apart from producing Y1, it also produces one intermediate step. As you can see that there's an outward arrow from this first RNN algorithm, right? Then the second RNN algorithm takes the second input, which is X2. It also takes the intermediate output generated by the first RNN block, and then it generates the second output, which is Y2 in this case. So as you can see, in time step 1, it will generate Y1, time step 2, it will generate Y2, and so on and so forth. Correct? Now, if we have to generate n tokens, so remember this X1, X2, X3 is not necessarily a word. It can be punctuation mark, it can be a segment of a word, anything. So in general, they are known as tokens. X1, X2 till Xn are the tokens. So if we have to generate n tokens, or if the RNN algorithm has to generate n tokens, then it has to spend n steps, right? N tokens will take n steps for both training and inference. Now, I hope in the previous session, I saw that you are learning how training happens, correct? Now, how training in probably that was more on like multi-layer perceptron or smaller neural network. But here also the training process is similar. Let's see how the training happens here. So again, whenever we have to train a model, then training a model means we have to update the weights, correct? Initially, before training the model, the weights are initialized randomly. Now, during the training process, the weights will be updated, right? Now, for training, we need to have golden labels. When we say golden labels, that means we have to know that if the input is the sequence of x1 till xn, then what should be the ideal output, which is y1 to yn. Okay. Now, initially, I mean, let's say the training started, we did a forward pass with x1 to xn, it will generate some value of y. Let's say the values are y1 prime to yn prime. And then those values will be incorrect, right? Because the RNN model has not been trained yet. Now, since the values will be incorrect, in the last step, we can take the error, like what's the difference between yn and yn prime, right? we can take that error and then we can back propagate. When we say back propagate, you can think that we're updating the weights of, we are saying that how much change in the weight is needed so that the desired change in output will occur, correct? That means we need to take the gradient of weights with respect to output and then propagate the gradient in the backward direction till we reach state 0 or the first RNN block, right? So here also you can see that if we have n RNN blocks, then we need n steps for training also. Fine. So that's all about RNN algorithm. Any questions so far? Yeah, so don't hesitate to ask questions. You can unmute and ask question. That's also fine for me. Now there are few problems for this RNN. So first problem is each output is produced at each time step, which is slow. If our sequence is long, then the computation is also long, right? That's one problem. But however, I mean, this problem is probably not big of a problem. The another problem is vanishing gradient. So remember, I was saying that whenever we are training the RNN, it will take n steps to propagate the gradients, right? And remember, all those gradients are the value, the absolute value of the gradients are typically less than 1. Whenever we propagate the gradient, they actually get multiplied with another number, which is whose value is less than 1, correct? Now you can imagine if we have like thousands of those RNN blocks. Now during backpropagation, we are actually multiplying. When we reach the first RNN block during backpropagation, we actually multiplied 1,000 numbers whose absolute value is less than 1, correct? That means the gradient value, the change in the weights for the very first block or the initial blocks will be very, very less, right? Because if all the values are less than 1 and then we are multiplying those values, the product will be very, very less than 1. Our product will be almost 0. This problem is known as vanishing gradient. It is very prominent if the sequence is long, right? If I have let's say 10,000 tokens in the sequence, then you have to backpropagate 10,000 steps. The gradient will be very small when it reaches the initial layers. So that's why the convergence will be slow during the training. That means since the gradient values are small, that means we have to update many, many times. We have to update the initial layers many, many times to make sure that there is some good update in the initial. This is one problem. Another issue is with RNN, there is difficulty in accessing information from long time ago. So let's say we are performing a text summarization task where we want to summarize a PDF where there are like, let's say 10,000 words or let's say 7,000 words, right? Now, as you remember, whenever we have this RNN algorithm, when we reach the last token as the input, then this last token, the last input token has almost no effect from the very initial tokens, correct? So that's not a good thing because usually whenever we read a PDF, whenever we read a long text, usually the context remains same across a long sequence, right? But this RNN algorithm is not so, it doesn't do so good with respect to long sequence. So these are few drawbacks of RNN, and due to, since RNNs has these drawbacks, that's why transformer algorithm came into the picture. This paper describes the transformer algorithm. Attention is all you need. You can go ahead and read the paper. Any of these AI tools nowadays, like any of the tools which is using LLM, Tech, Gemini, DeepSeek, Copilot, anything, ChatGPT, anything, they all use this same concept. Attention is all you need. Like on top of that, yes, they have other engineering techniques which probably make the models more efficient. But the backbone model is transformer-based model, which is coming from the paper Attention is all you need. Before we go there, is there any question on RNN training inference or in general? Okay. So now we will discuss what is so special in this large language model algorithm that they are performing so well for all these sequence to sequence tasks. So in this picture, you can see that there is like many computations. Some computation is part of encoder and some computation part is part of decoder. So this is called a encoder decoder architecture. And usually in this transform algorithm, there is no single encoder or single decoder. There are more than like one encoder. There can be like any any number n encoder and decoder. Okay, so this transformer algorithm is based on encoders and decoders. Also, you can see that they are connected. Encoder and decoder are connected. Input to the encoder is a sequence of word. Here we see that this is the input to the encoder, which is a sequence of word or token in general. That can be a sentence. And input to the decoder, there are three input to the decoder. One is outputs shifted right. We will soon see what does it mean that shifted right output. Then we have output probabilities, and then the input to the decoder is also one input to the decoder is also coming from the encoder. Okay, so that's the basic structure. Now what we will do is we'll go into each of the components of encoder and decoder and see what do they do. Okay, or how what is the main requirement of different component of encoder and decoder. So in this figure, I mean, in this figure is like cut version of the entire encoder decoder model. So here I am showing the first step is input embedding. Okay, so inputs are coming again. Inputs are nothing but sentence or sequence of tokens or words. Now the first step is input embedding. So in this input embedding, the task is to tokenize a sentence. Remember, whenever we put a sentence into the machine, into the computer needs to know. I mean, computer only understands in terms of numbers, right? Binary numbers, correct? So we have to somehow encode all those words into numbers. So the first step is, or the process is called tokenizing a sentence. It not necessarily into words, it can be in different tokens. So let's say we have this sentence, your cat is a lovely cat. Okay. Now, in this input embedding step, the first step is to assign ID to each token from a dictionary. So you can think that whenever we as a human being try to understand a word in any language, the first thing we do is try to get the meaning of the word, right? So inherently, we have a dictionary in our mind, correct? Now, from that dictionary, we try to take the meaning of the word. Okay. In input embedding step, the same thing happens. The LLMs are also trained with some dictionary, and you can think that the dictionary has, if the dictionary has, let's say, 10,000 words with ID from 0 to 9,999, then each of the token have unique ID, right? So that's why you can see that your cat is a lovely cat. Each of the token will have some ID. Now, of course, if the word is same, then the ID is also same. Right? Cat in this sentence, the word cat is used twice, and they have the same ID. Correct? Now, of course, the ID is not the only thing, or not the only thing required to differentiate between tokens. Those words or those IDs are mapped to some vector. Okay, that means each of the token has a vector representation, and as you can see that the length of the vector can vary. The length of the vector is typically represented by this D model. For our example, we will take the D model size as 512. We will take the D model as 512. So remember, this embedding is not part of LLM training. Okay, so embeddings are learned separately. I mean, there are like different kinds of word embedding. So any LLM can take any of those word embedding, and then the LLM weights can be learned. Okay, so that's why we are not going into the details of how these word embeddings are learned, but those numbers are also learned. So you can think that each word or the whole dictionary, each of the word in the dictionary is represented with a 512 dimension vector. Okay. So again, I mean, this represents the meaning of the word, their learnable parameters. As I was saying that if we have same word, they will have exactly same representation, because again, if we go to a dictionary, you will find the same word in the same position all the time, correct? So that's the reason that this word cat has exactly same ID 6587, and of course the same ID maps to the same vector. Okay. So far, what we did is, yes, there is a question. Let me read the question first. Can the embedding models like Gemini embedding or Quine embedding models used here? Yeah. So those are the embedding models for the encoder. So another thing is that although I am describing this encoder decoder model, but the latest LLMs are decoder only model. But again, even if we have decoder only model, the words need to be embedded first. And you are correct, yeah. So any of those Gemini embedding or Quine embedding can be, I mean, they are like different types of embedding. That's all. Any other question? Okay. And yeah, I mean, don't worry if you want to unmute yourself and ask questions. So far, we have seen that given a word, we are trying to extract the meaning of the word from a dictionary, which is good. But then, as a human being, um, when we try to understand the meaning of a sentence, we actually do not just try to understand the meaning of each word, and then from the meaning of each word, we don't understand the meaning of the sentence. Rather, what we do is we try to see how different words are placed in the sentence. For an example, I am at the FDP versus am I at the FDP. Both the sentence use the word am and I, right? But then depending on the position of the word I and am, the meaning of the sentence changes, right? Although we will get the exact same embedding for am and I for both the sentences, but both the sentences have totally different meaning or totally different context, correct? That's why just the meaning of the word is not sufficient, but the position of the word in the sentence is also required. And that's why encoder, the next block of the encoder is positional encoding. So the idea is each word should carry some information about its sentence, and embedding doesn't carry any info about the position. So far in the previous step in input embedding, they just carry the info of the ID, where the word is used or where the word is placed in the dictionary, right? They don't have any info about the position in the sentence where the word is used, right? That's why the authors of the paper figured out a solution. They told, let the model treat words that appear close to each other as close, and words that are distant as distant, right? Now, the positional embedding provides a pattern that a model can learn. We will soon see what is positional embedding, but remember this positional embedding vector is not learned. Unlike input embedding vectors are learned, but positional encoding vectors are not learned. They solely depend on the position of the word. Right? So let's see how are they calculated. So this positional encoding is just a function. It takes the position. Position is nothing but the position of the word in the sentence. If the sentence length is, let's say 1000, this position value will be changing from 0 to 9999. And I is the index of the vector. So remember that this input embedding vector will be added with positional encoding, right? That means if the input embedding vector is of size 512, the positional encoding size is also 512. And that 512 is nothing but the embedding size or the hidden dimension. Different places call it differently. Now, this I is the index of that position in the vector. So for an example, let's take two different segmentation of two different sentences. One segment of a sentence is your cat is, and another segment is my dogs are, right? Now, of course, all the words are different here. Like your cat is, my dogs are. All the three words are different from each other, right? First word is your. First word is my. They will have different meaning from input embedding, yes, but then when it comes to positional encoding, they will have exactly same number. So for an example, this year will have the value from P0, 0 to P0, 511. The first zero, the first index denotes the position of the word in the sentence, and the second index denotes the position of the value in the vector. So since our embedding dimension is 512, that's why it is varied from 0 to 511, right? And for odd position, or for even position, sine function is used. This is a sine function. For odd position, cos function is used. So yes, I mean, as you can see, there's a specific like structure of the function. So in the paper, they describe why we need the specific structure. Now, more importantly, if we have two different sentences with two different set of words or tokens, they might have different input embedding, but then the words in the same position of those two different sentences will have exactly same positional encoding. For example, you can see that for your, the positional encoding will be P0, 0 to P0, 511. For my also, the positional encoding will be P0, 0 to P0, 511. The same positional encoding for all sentences will be there. So that's how positional encoding is calculated. And as you can see that input embedding doesn't capture any information related position, but positional encoding is solely used to capture the information related to the position of the word in a sentence. Fine. Any questions so far? Okay. Now the next step is to add this input embedding and positional encoding, right? So again, we had this sentence, your cat is a lovely cat. From there, we got the embedding. If we assume that the D model of the embedding dimension is 512, then each of the word will have a vector of size 512, which will be added with the positional embedding. Sorry, positional encoding. This is wrong. This will be positional encoding. The positional encoding vector is also of size 512. And then remember, the positional encoding is just computed once and reused for every sentence, right? Any sentence comes, it will use the same positional encoding vector. Now, these two vectors will be added for each of the word, and then whatever we will get, that will be the input to the encoder. So if we have this sentence has 6 tokens, and each of the token is represented by a vector of size 512. So the input to the encoder will be a matrix of size 6, 512. So that's the input to the vector. Input to the encoder. Now let's see what is there inside the encoder. Now inside the encoder, the first block is attention. Although the first block is multi-headed attention, but before we discuss multi-headed attention, let's discuss what is self-attention. This concept of self-attention was actually introduced before the introduction of transformer algorithm. When this transformer algorithm came into the picture, multi-headed attention was introduced, and which actually changed the efficiency of this transformer algorithm. We will see what is multi-headed attention and all. But before that, the self-attention is just a function. This function takes 3 input, Q, K, and V. And the function says, if we have this 3 input, it is nothing but softmax of QK transpose over square root of DK multiplied by V. Okay, that's all. I mean, self-attention allows the model to relate words to each other. We'll see how. And then we will consider a sequence length of 6. When we say sequence length of 6, that means the sentence has 6 tokens. And let's say D model, the hidden dimension is 512. Now, as you can see here, the sum of positional encoding and input embedding is replicated thrice, right? So these three are nothing but the QKV. Let's say it is X. We are getting X here after we add this position and putting in input embedding. In that case, all this QKV will be equals to X, which is nothing but the input sequence. I mean, input sequence passed through the input embedding in position encoding. So the first step is softmax of QK transpose square root of DK. Q is of size 6,512 because we have 6 tokens in the sentence and each token is represented by a vector of size 512. Okay, so that's why that's the input, that's the size of Q. And again, K is same as Q because we assume that the same input is replicated thrice. So K transpose will also have a size of 512,6. That will be, these will be multiplied over square root of 512. So if we multiply this to matrix, we'll get a matrix of size 6,6, right? And on top of that, we will apply the softmax. Softmax is applied row wise. So whenever we apply softmax on a series of numbers, then it changes all the numbers to a probability value. So you can think that yeah, in this case only you can see that we have this 6 by 6 matrix after softmax. Softmax has been applied on each of the row. Since each of the row denotes some probability values, the summation is 1. The row wise summation will be 1. Now, if you look closely, what we are actually doing here, so if you remember, I mean, in physics, we studied about projection, right? The dot product. The dot product between two vectors is x multiplied by y transpose or y prime, right? So when we do dot product, if we have two vector and if we are doing dot product, that means we are trying to project one vector on the other, right? So here also, when we do QK transpose, we are trying to project one sentence or one query on each other. So that means we are trying to get the relation of the words inside in the sentence, relation between the words in the given sentence, correct? So that's what QK transpose is doing, and then softmax is there to make it nonlinear. The next step is to multiply with V. Again, remember Q equals to K equals to V. So the size of V is also 6,512. This V is getting multiplied with a matrix of size 6 by 6, which is nothing but softmax of QK transpose. And as a result, we are getting this attention scores, which is again of size 6,512. Now, if you look closely, you will understand that each row in this matrix, this attention matrix, captures not only the meaning given by the embedding or the position in the sentence represented by positional encoding, but also each word's interaction with the other one. So now we are actually trying to do cross interaction between the words, which was not there in RNN. In RNN, it was always the words were always analyzed in the forward direction, if you remember, right? So this is one reason why transformers are better, but one of the reasons. I mean, there are many other reasons. We'll see more of them. Now, there are some specific properties of this self-attention function. So remember, this self-attention is permutation variant. When we say permutation variant, that means if you take a sentence, compute the self-attention score, and then if you shuffle the words, the values will not change. You will see that just those values have changed the position. So that's why it is called that it is known as self-attention is permutation invariant. Self-attention itself doesn't require any parameter. Remember, it just takes three. When we say parameter, that means we mean the trainable parameter. Self-attention just takes three values or three input, QKV, and then it computes softmax of QK transpose over square root of DK, right? Values along the diagonal are the highest. This also can be proved. But this also means that one word has the highest correlation with that word itself, right? And the final property is if we don't want some position to interact, we can always set their values as negative infinity. Eventually, softmax will make it to 0. So we will again see, so we will soon see that why we do, when is the case when we don't want some person to interact. So these are the properties of self-attention. Again, self-attention is just a function. It doesn't need any parameter, the trainable parameter. It takes 3 input QKV and then computes softmax of QK transpose over square root of DK multiplied by V. Any questions so far? Okay. Now, so yeah, so far so good. Self-attention is allowing us to compute the correlation between different words in a sentence. But remember, when we as a human being try to analyze a sentence, we actually analyze into different contexts. Like let's say we're reading newspaper, or nobody reads newspaper nowadays. Let's say we just got a WhatsApp forward with some news. We're trying to understand whether this news is positive or negative, whether this news is fake or real, whether this news will affect myself or not. So we're trying to analyze the same sentence or same piece of text in multiple contexts, right? That's why this multi-headed attention came into the picture, which changed the efficiency of all these transformer algorithms. So as a reminder, self-attention is nothing but it takes 3 inputs QKV and then it computes softmax of QK transpose over square root of DK multiplied by V. When we have multi-headed attention, it also takes 3 input QKV, the same QKV input. It is expressed as concatenation of head 1 till head H. Here we say that there are H heads in the algorithm multiplied by WO. And each of the head is nothing but attention of QWQ, KWK, VWV. Now you can see that QKV are multiplied by some weights, and then they are passed to the attention. So earlier, all the QKV were exactly the same, which is nothing but input passed through positional encoding and input embedding. But here, the input is multiplied with 3 different vectors, and then they are passed to this attention function for each of the head. Now let's see how it actually works. So again, we have, let's say, input. The size of the input is sequence comma D model. Sequence is nothing but how many tokens are there in the sequence. D model is 512 in our example. So that input is QKV replicated thrice. Now this Q is multiplied by WQ, K is multiplied by WK, V is multiplied by WV to obtain Q prime, K prime, V prime, right? Now the next step is in multi-headed attention is to segment this Q prime, K prime, V prime in D model axis, right? So that means every head will see the full sentence, but smaller part of embedding of each of the words. So for an example, if Q prime was of size, let's say 6,512, and if we have 4 heads in the model, then each of the head Q1, Q2, Q3, Q4 will have a size of 6,128. So each of the head will have all the words, but then a different part of the embedding, right? So similarly, K prime is also cut into 4 heads, segmented into 4 heads. V prime is also segmented into 4 heads. Now that we have Q1, K1, V1, on Q1, K1, V1, we apply the attention. That means we'll have the softmax of Q1, K1 transpose over square root of DK. Again, this DK is nothing but D model over H, okay? Because DK is a smaller head. So we apply this attention on Q1, K1, V1, Q2, K2, V2, Q3, K3, V3, and Q4, K4, V4 to obtain head 1, head 2, head 3, head 4. After that, we have this head. After that, we concatenate all the 4 heads to get this concatenated head. Once we get that, we multiply with another set of weights, WO, to obtain this multi-headed attention. That's how the entire computation is being done. Okay. Now let's see how we can actually visualize that. Let's say we have a sentence. It's in the spirit that a majority of American governments have passed new laws since 2009, making the registration or voting process more difficult, period. And then we have this end of a sentence, and then all the other position of the sequence is padded with 0, right? Now, let's say that we have applied attention on this, or we have applied multi-headed attention on this sentence. After that, we're trying to visualize each of the head with respect to this word making, right? Now we can see the same sentence is written again here, but then there are some colors, right? If you closely see that the word difficult has many colors, but for all other words, maybe difficult and more has many colors, but some maximum of the word has no color. If you look more closely, you will see that there are 8 colors for the word difficult. That means there are 8 heads for this algorithm, and each of the color denote the value. So if the color is bright, that means the value for that head is higher. That means making is strongly correlated with this word difficult in many of these contexts. Again, a different head denotes different context, right? Similarly, making is also correlated with more in many different contexts. But then if you see, making is barely correlated with 2009. Only one color is bright. That means only one context is relevant between making and 2009. Okay. Then making and laws have very faint color. That means it has very little correlation between them. All the other words have almost or zero context, almost no context or zero context with respect to making. That's how we can actually visualize this attention. Any questions so far? Okay. Now let's see what are the other operations. I mean, other operations are not too complex. After that, after multi-headed attention, we have add and norm. I mean, we just add the input to the output of multi-headed attention and then normalize it. It's also used in deep neural networks. Now, okay, after that, feed-forward network is there. Feed-forward network is something like multi-layer cluster trunk. Now let's talk about the decoder. So far we have talked about the encoder. Now let's talk about the decoder. So output embedding is similar to the input embedding. I mean, you can see that there is some output embedding, which is similar to the input embedding thing. But here we have something called masked multi-headed attention. We will soon see what is masked multi-headed attention. Now here in this multi-headed attention, you can see that keys and values are coming from the encoder, right? And the queries are coming from the self. So that means it is no longer self-attention, it is cross-attention. It has then fully feed-forward network, which is nothing but a fully connected layers, which is a fully connected layer. Now remember, whenever any of these tools like ChatGPT or Gemini or any of these tools, whenever they are trying to like generate tokens, it doesn't know what will be generated like 10 steps later or in the future, right? Only when it generates the token at nth step, then only it can generate the token at n plus 1th step, correct? So that's why the goal of the decoder is to make the model causal. That means output at a certain position can only depend on the words on the previous position. So for example, when we have the word cat, it doesn't know that the future words will be is a lovely cat, right? It can only know, or it can only compute the correlation with respect to the previous words. So we have to make the model causal. So that's why what we do, or what is done in decoder or in the attention computation, all the future words with respect to one particular word, all the, like after softmax, all the values are replaced with negative infinity. If we make this word value as negative infinity and then create the probability or modify or convert it into probability values, then all these values will be 0, right? And that was one of the property of self-attention, that if we want to make the values 0, we can just set this to negative infinity, and that this is where this property is being used. Okay, so this is called masked multi-headed attention, where you set the future values as negative infinity, so that after softmax they will be 0. Now let's discuss how the inference happens, how actually the inference happens. Let's say the inference task is translation task from English to Italian. The English sentence is "I love you very much." The Italian, in the Italian, it translates into "Ti amo molto." Okay. Now in the encoder, so another important aspect is every sentence has to be appended with start of a sentence and end of a sentence, so that the computer knows when the sentence started and when the sentence is finished, right? 1 second. Yeah. So let's say in the encoder, we have provided the input SOS, "I love you very much." It will go to the encoder input. All the embedding, encoding will happen. Then encoder output will happen, which is fed to the decoder. Now, in the decoder, the first token is SOS, start of a sentence. That has the first token has to be start of a sentence always. So with this SOS, with this first token and the encoder output, all the decoder computations will be there. Everything will happen, and then the model will generate the first token as T. Okay, that's the first translated token. Now in the next step, in step 2, that T will be appended into the decoder input. So this is now SOS T. Okay. Remember, we have the encoder. The encoder input is the same. Since the encoder input is the same, encoder, all the weights are the same, we do not need to compute, right? We can just store the values, the final values, and then pass it to decoder, correct? We can just cache the values. Now with those values and then with these input SOST, the decoder will generate the next token AMO at step 2. Now then step 3, it will generate molto, and then eventually it will generate end of a sentence. So that's how all these large language models actually generate the sentences or generate the tokens. It will take an input, it will process through encoder, or it will do some processing, which is known as pre-fill in a decoder only model. Then the decoder will generate one token at a time. The generated token will be appended to the previously generated sequence. With that previously generated sequence and the input to the encoder, decoder will generate next token. So that's how inference happens in any LLM. Like you use ChatGPT, Gemini, anything you use, it's the same process. It's exactly the same process. That's all about inference. Now let's see how the training happens. Remember, for training, we have to give all the input, right? Again, same input is the SOS, "I love you very much." And here we have to provide what is the output, SOS Ti amo molto. In the output of decoder, we have to give the shifted version, because remember, when the input to the decoder was SOS, the output was T. When the input of the decoder was SOST, output was AMO, correct? That means the output will be shifted version of the label, correct? So this is more like better representation. If we have SOS Ti amo molto, with SOS we generated T. With T, the golden output is AMO. With SOS Ti amo, the golden output is molto, and so on and so forth. Now, if we have this, what we can do that, again, the regular training process, all the values will be computed. Then at the end, something will be generated which is not correct. So we can just take the error between the golden output and whatever was generated. Then we can have the cross entropy loss, do the backpropagation to update all the weights. That's the training process. Now, here, the most important thing is we can train one whole sequence at once. It all happens in one step, unlike RNN. If you remember in RNN, if you want to train with a sequence of, let's say 10,000 tokens, then you actually had to spend 10,000 steps. There was no other way. But in transformer model, you don't need to spend 10,000 steps. You can just spend one step and then you can train all your weights. That's a huge gain. And that's why nowadays we can actually see like trillion parameter model, which was not which was impossible to train earlier when our model was RNN. Since we can train this trillion parameter model, that's why we are able to produce big model which can do many of these tasks, right? Any questions so far? Okay, so if there is no question, I mean, I will move to the next topic, but I'll just take 5 minutes of break. I will exactly start at 3:06. Sorry, I took a longer break. Yeah, let's get started. Before that, any question? Does anyone have any question? Okay, so far we discussed that how this large language model work, and I mean you can imagine like if we have, okay, there is a question. Let me see question. If you are starting our AI career, okay, fine. This kind of, I will take this kind of question in the end. Okay. Any other question? Any other technical question? Okay, fine. So yeah, so far we discussed how this large language model works. First, input embedding, then position encoding, then all those attention will be there. We also saw how training and inference works. Now, the main important thing is, even we have these big models. I mean, even if we have these models, there is like huge number of computation, right? In our example, we are using the embedding size as 512, but for the newer model, the embedding size can be like 2048 or something like that, right? And then if you have a sequence of like 1,000 or maybe 7,000 words, then your matrix dimension is easily like 2048 by 7K. That's huge, right? If you want to do multiplication, all those were matrix multiplication, right? If we want to do matrix multiplication, then like it's huge number of matrix multiplication. Correct. Now, I mean, however, I mean, as a user, we want answers very fast, right? I mean, whenever we put a prompt on ChatGPT, we want the answers to be shown very fast. How can it be done? I mean, we have too much computation, and remember, all those computations are happening, although GPU, but those has to happen, right? That's why there are many work which try to lower the computation burden of this large language model. Lean Former is one of them. There are many. We'll just discuss 2 or 3, which should encourage you to look more. Now, in this Lean Former, the main goal is to reduce the complexity to order of n. If you remember, we had in multi-headed attention, each head was nothing but attention of QWQ, KWK, and VWV. That is softmax of QWQ multiplied by KWK transpose over square root of DK multiplied by VWV, right? Now, computing this inner matrix, this QWK multiplied by KWK is expensive. The complexity is order of n square, where n is the sequence length. And sequence length can be very big. Like you can see what's the sequence length of today's models like Gemini and all. They have easily 16K or even 32K as sequence length. Now, here the authors observed that self-attention is low rank, which means many rows of P are almost dependent to each other. So that means we can actually do a single value decomposition and then bring the matrix sizes lower. So specifically what they do is they modify each of the attention computation. And so they introduce this EI and FI projection matrices where they are of size n by k. In this case, k is very less than n. Okay. And if we do that, it will be like softmax of QWK, EI multiplied by KWK transpose over square root of DK multiplied by FI, then VWV. If we look closely, the dimension of the inner matrix is now n by k instead of n square, right? That means the computational complexity is order of nk, which is almost similar to n because they show in the paper that k is order of d over epsilon square, and d is the embedding size, which is independent of n, right? Embedding size is the model property. It has nothing to do with the sequence length, correct? So that's how we can reduce the dimensionality of the matrix multiplication, right? Now, two things. Whenever we do this kind of optimization, we are changing some numbers or we are changing the multiplication, right? With a hope that the complexity of the computation reduces, correct? Now, if we do that, we have to first show that the accuracy remains intact. And of course, we have to show that how much computation we are improving or how much computations we are reducing. That's why the authors also first show the accuracy. So the first row is the accuracy of the base model on different data set. And like, as you can see, the average accuracy is 92.25. Then they show the accuracy when this n, sequence length n, is projected into different dimensions, 128 into 56. You can see that the average accuracy is almost the same. There is no major degradation in the accuracy. Similarly, in BERT-based and link for BERT-based model also, the accuracy remains the same. So accuracy-wise, there is no issue. That also means that the observation authors made that this self-attention is low rank, and then we can actually reduce the dimensionality. That observation is correct. Now let's see what's the improvement in efficiency. Remember, all these low rank computation or low rank conversion was done because low rank conversion was done with a hope that the amount of computation will be lower. The amount of computation will be saved. Number of computation will be lower. Now they show two things: time saved and memory saved. Remember, if we have large matrix multiplication, that will also need large memory, right, to save all the intermediate values. Now here they show the savings when different sequence length is projected onto different dimensions. This n is the original sequence length and k is the projected dimension. So if we have a big sequence length, 32768 in this case, and then if we project onto a very small dimension, then the savings is higher, 13 times, right? But if we project into a higher dimension, then the saving is lower, which is intuitive, five times. So that trend is there always. And as you can see, I mean, with 8192, the savings in time is 5.5 times when we have projected into 128. There's a question here. The length n is the same as the context size. Yes, you are correct. That's the sequence length, not context size. I won't say context. Okay, yeah, you can say context size. Yes, because that's a sequence. Correct. And then the similar result can be shown, it can be seen in memory saved. If we have the sequence length of the context length, if that is projected onto a lower dimension, the memory saved is higher. Now, of course, this 56 times, these numbers are very, very impressive, right? I mean, this is the memory saved, but if you see this time saved, we have time savings like 8.9 times to 3.3 times. Like, let's say previously, whatever was taking 1 second, it will now take a few milliseconds, right? Which is very impressive. So that's how you also should do, I mean, your optimization. If you're proposing some optimization on top of these LLMs, then you should first show that the accuracy remains the same. And then you should show that the improvement is huge. It should not be marginal improvement. This is one work. Then another work is called as flash attention, which is acceleration of training, which is a technique which accelerates the training. So we already discussed that the standard attention implementation is nothing but attention of QKV, which is equals to softmax of QK transpose over square root of DK multiplied by V, right? Now again, remember this matrix sizes are, the size of these matrices are very, very big, like QK and V are the very, very big. Now in a computer, whenever we perform the multiplication or whenever we perform any computation, the data always needs, or most of the time, the data needs to be loaded from a main memory, which is known as RAM. Technically, it is known as HBM, DDR3, DDR4. There are many types of main memory. The data needs to be loaded from main memory, brought into the compute, and then only we can do the computation. Now, whenever we say brought into the compute, they have to brought into the cache, which is sitting near to the ALU, near to the compute unit. So remember, the cache size is very small. We cannot load the entire, there's a very less chance that we will be able to load the entire QK matrix from HBM to the cache, right? So that's why we have to bring those values in blocks. We have to bring those matrices in blocks. Now, another important thing is this transaction between main memory and the processor is expensive in terms of latency as well as energy. Whenever there is a transaction between the main memory to the processor, the transaction happens to the PCB, to the wire. That is not energy efficient, right? But we have to do this transaction because the cache is not sufficient to hold all the thing required for the processor, right? Now, if we want to do this attention computation, then we will first load QK by blocks from HBM. We'll compute this partial sum, then write partial sum to HBM. Then again, read this partial sum from HBM, compute P is equal to softmax of AS, write P to HBM, again load P and V by blocks from HBM, compute O is equal to PV, write O to HBM, then return O. This is the whole step of standard attention implementation. Now, as you can see, there are lots of memory access, be it read, be it write, but there are lots of memory access to and from HBM, which increases the latency of the entire computation. And remember, whenever we are doing the training, at each training epoch, we have to perform this matrix multiplication. So if we have a training task, and then if we are doing this, then definitely it will increase the training time a lot, correct? That's why the flash attention proposes something called tiling. So they split this QKV into blocks. So instead of multiplying the whole QK transpose multiplied by V together, they split QKV into the blocks. They load those blocks from slow HBM to SRAM, compute the attention output of the blocks, but that will require extra statistics. So remember, this is not just plain multiplication. There's a softmax in between, which is a nonlinear operation, right? If it was a plain multiplication, then probably we could have just multiplied the blocks and then somehow add the partial computation, which is from the blocks, right? But since we have this nonlinear operation, we need to require extra statistics for softmax. This is one optimization proposed by flash attention. Another optimization proposed by flash attention is recomputation. So remember, whenever we perform training, we need the activations which were computed during the forward pass, right? So that's called those activations are required to compute the gradients, right? We can store the gradients. And we can reuse during the backward pass. But remember, in LLMs, if we want to store, that will take like hundreds of GBs of space because the matrix sizes are too large, right? That's why the flash attention says, or the authors in flash attention proposes, that we shouldn't store. Rather, we can again recompute. We can again compute the same activation. If we do that, then we don't need to actually store them. If we recompute, then we will save on memory. Remember, whenever we say memory, even if we want to reuse, we cannot store them in the cache because the cache sizes are barely in MBs. We have to store in the main memory. During backpropagation, again, we have to load them from main memory, which will take huge latency and energy. Now, this is the flash attention algorithm altogether. I'll not go into the detail, but as you can see, it takes this matrices QKV, which is staying in the HBM. Then the on-chip SRAM of size M is also given. So first, they compute what's the block size for Q, K, etc. Right? And then they divide Q into TR blocks, KV into TC blocks. After that, they load these blocks one by one. So you can see that it is power 1 less J less TC. So that means they will load this KV one by one. Now for each of these K and V, they will load these Q blocks of Q. Now, apart from blocks of Q, they also need to load these output, the block of output along with the extra statistics from the HBM to on-chip SRAM. They have these extra statistics. Again, this extra statistics is required to do the computation exact. I mean, there is no approximation here. There is exact computation. So for that, they need these extra statistics. Now, finally, you can see that they are writing this O to HBM, L to HBM. Now, if you look closely, the number of HBM access is very less. So they just loaded from HBM to SRAM all the QKB once. They are writing also once. In the previous one, there were lots of HBM access. And if we reduce the HBM access, then definitely we will reduce the latency. Now let's see the result. So here they don't show accuracy results because they are not doing any approximation. The calculation is exactly the same. So to get this result, they have performed this forward plus backward runtime. This is of standard attention and flash attention for GPT-2. GPT-2 medium, where they have sequence length of 1024, head dimension is 64, there are 16 threads, batch size of 64, and 800 GPU. 800 GPU is one of the GPU from NVIDIA, which is like fairly advanced. Now, as you can see, they have compared three metrics. One is gigaflops, then HBM read write and runtime. So the standard attention has 66.6 gigaflops. Gigaflops is nothing but number of floating point operation. Giga is nothing but 10 to the power 9. So number of giga floating point operations. So since flash attention does this recomputing during the training, the number of gigaflops has increased from 66.6 to 75.2. So it's almost like 15% increase in computation. Now you can say that, okay, what was the point then? If it increases the computation, then it will increase the latency, but no. Although it increases the computation, it reduces the number of HBM read write, the main read and write required to the main memory a lot. So that's what it is shown in the second row. In the standard attention, the HBM read write was 40.3, but in flash attention, the HBM read write is only 4.4. It's like 9 to 10 times improvement or reduction in HBM read write. Since there is a huge number of reduction in HBM read write, the runtime also reduced from 41.7 to 7.3 milliseconds. That's a 6 times improvement, right? Or maybe 5 times. That's also a huge improvement. Now, as you can see, the very interesting fact is they're increasing the computation. So we may always think that if we have two algorithms, if one algorithm has more computation, then definitely it will take more time. But practically, no. Sometime it may happen that the computation or the runtime is actually bounded by memory. So it may happen the algorithm is memory bounded. And it turns out this attention algorithm while training is actually memory bounded. So that's why even if they increase the computation, since they are reducing the memory operations by a huge margin, they have significant reduction in runtime. And that's a very important takeaway. I mean, if we want to improve some algorithm in terms of runtime, we may not need to reduce the computation. Sometimes increasing computation, but reducing the memory actually will help us a lot. Okay, so that's all about flash attention or the acceleration of attention. Any questions so far? Okay, so with that, let's discuss something about speculative decoding. And again, remember this speculative decoding flash attention. Does any of the latest model use flash attention? All the latest model uses flash attention. So, mainly it is used for training, but there are, okay, whatever I discuss is the first version of flash attention. There are flash attention 2, 3, etc., which is further improvement on top of flash attention. But yes, any model nowadays or any company which are building these models nowadays, they use flash attention for training. Does reducing attention complexity in lean former affect contextual understanding? The short answer is no, because that's why we saw that there is not much reduction in accuracy, right? So if there is not much reduction in accuracy, that means there is not much reduction in this contextual understanding. Any other question? Okay, fine. So with that, let's discuss about speculative decoding. Again, speculative decoding is another technique which is used by all the AI tools nowadays. So just to give you a refresher, let's say we have a query or pre-fill, whatever you name it. The query is the cat sat. If we give it to the encoder, or let's say that in the decoder only model, it's just decoded. If we give it to the decoder, then it will compute first, and then it will generate a series of probability for different tokens, right? There is a question, let me answer that. If flash attention is exact and efficient, does it remove the need for approximate attention methods like linformer? So it doesn't remove the, I wouldn't say that it removes the usage of linformer. You can always use the linformer on top of flash attention, right? So even if flash attention is there, still the QKT computation is there, right? And linformer is actually saying that we will reduce the QKT computation complexity. So it doesn't, they are kind of orthogonal technique, and they can be used together. Okay. 1 second. Yep. Now, how actually this decoding happens? Given this prompt or pre-fill, we will have at the very last layer, we'll have probability for all possible tokens. Now, whichever token has the highest probability, that token will be chosen. So let's say the highest probability is seen for the token on, the next token or the next word will be on. Now again, with this, the cat sat on, we will again compute the probabilities through all those encoder decoder computations. Okay, we will compute all the probabilities for different tokens, and then see that which token has the highest probability. Let's say the highest probability is with token R, so we'll choose the word R, the token R as the next token. And let's say the next token is Matt. After that, we have end of sentence, right? So that's how this decoding happens, or that's how the tokens are generated. So here we generated the cat sat on a Mac, correct? Now, clearly, we generated 1, 2, 3 tokens, right? On a Mac and then end of a sentence. So remember, this end of a sentence is also a token which has to be generated, correct? So clearly, we had 4 forward pass, and then in 4 forward pass, we generated 4 tokens. Now, the question is, I mean, in general, if we want to decode K tokens, it will take K serial runs, right? Now, the question is, can we somehow decode several tokens in parallel, right? So that we don't need to wait for K serial runs. Can we decode several tokens in parallel? So let's see whether we can do that or not. So let's say we have a guess. Let's say the prompt is the cat sat, and then someone magically guessed the rest of the tokens. And let's say the guess is nothing but on the chair end of a sentence. How and where the guess from where the guess is coming, we will discuss later. But let's assume that there is a guess, right? Now, remember, if we have a guess, we have to verify the token. We have to verify the tokens from the guess, right? We cannot just take the guess as output. Now, to verify, we do not need to pass all the tokens one by one. We can actually provide the whole sequence to the LLM, and then we can generate all the probability values together. So remember, it is at the end of the day, they are all matrix computation, right? So instead of generating one token at a time, during verification, we can actually provide the entire sequence to the LLM and then generate the probability values. So it will then generate generate the probability. It will generate the probability values with respect to all the previous tokens. Remember, these are all masked attention, right? So for this word sat, it will generate the probability values which should be there for the next token. and the token with maximum probability is on, which matches the guess. So we'll keep it, we'll accept it, right? Now with the word on, again, we see the token with the maximum probability is A, but that doesn't match with our guess. So we will reject it. So remember, all the tokens have been guessed and we are verifying in parallel, right? So all the probability values have been generated in parallel. Now we are just checking, we are just verifying whether our guess was correct or not. So we reject the case and then we will say, okay, the is not correct. We will do a, we will put a, right? Now, since so far what we have done, we have just done one forward pass, right? Why one forward pass? Because we have the whole guess. From the whole guess, we just did one forward pass through the LLM to generate all these probability values. So we just performed one forward pass, but generated two tokens, which is a gain, right? Earlier, if we are doing one forward pass, we were able to generate only one token, correct? Now here we performed one forward pass but generated two tokens, which is on and off. Now since the guess here was the, and most likely this word chair was dependent on the, that's why we will not take this chair. We can't use the rest of the completion, as it was dependent on token the that has been rejected. So since the was rejected, we'll discard all the tokens, right? And as you can see that our new input prompt will be the cat sat on a. On was correctly guessed and a was generated by the LLM in the position of this the, right? And again, we will continue this guesswork, right? So we will continue this guesswork, and then we will probably in the next iteration we get this guess table, right? After table, we are having this end of a sentence. So again, these are the guess, and eventually we will also need to verify this guess, and so on and so on. So the main motivation or the main crux, the main idea is here we just performed one forward pass but generated multiple tokens, right? Now the question is, how should we guess? How should we have the guess? The answer is the guess is also done with another LLM, but with a smaller LLM. So let's say the idea is, let's say we have this 100 billion parameter model, okay? Now some tokens are very easy to guess. The idea is, why do we need that 100 billion parameter model to get those easy guesses or get those easy tokens? We do not need. So let's say I say my pre-fill or the prompt is I am at Indian Institute. It is very easy to guess the next token, which is off. But then it is difficult to guess the token after off, because it can be I am at University of Science, University of Management, University of Technology, wherever. It needs to know the context and all those things to guess the next token, which is science, right? But the idea is, if we have some tokens are easy to guess, we do not need a large model to guess those tokens. Some tokens are really difficult to guess. We should use a large model to generate those tokens. So similarly, let's say this is a Hebrew to English translation task. In Hebrew, this is the input, and English, let's say the translation is the president was Barack Obama, right? Now here, it is very difficult to guess this word president. If you don't know Hebrew, if you don't know the context, you cannot generate this word president, or if you cannot guess this word president. It requires looking several tokens back, knowledge of Hebrew, etc. But as soon as you saw this word Barack, it's very easy to guess that the next word or the next token will be Obama. We actually do not need a billion or trillion parameter model to guess the next word of Barack, which is Obama, right? We can guess based on just the last token. So we do not need a token which takes large context length or large sequence length. We can have a smaller model which takes a smaller context length to get the word Obama. So that's how this speculative decoding works. So in this case, as you can see, we are speculatively decoding some of the words. So the takeaway is you can use a much smaller draft model to guess easy tokens. Another example is, let's say we say a group of flamingos is called, let's say we have a draft model. Draft model will say a flock, but that is not correct. But guessing this word is very easy, right? However, flock, to know the correct word which is represented when the group of flamingos, whatever the group of flamingos is called, it needs a knowledge. So the group of flamingos is called a flamboyance, which is difficult, right? For to know that or to generate that word flamboyance, we need we need a bigger model. But to generate this word we do not need a big, and that's the main intuition behind this speculative decoding. Now, this is another example. Let's say the example is, the whole sentence is Japan's benchmark Nikkei 225 index rose to 26.69 points or 1.5% to 10,989.79 in late morning trading. And that's the whole sentence has to be decoded or has to be generated. And we have used speculative decoding, let's say. Also assume that we are speculatively guessing 5 tokens at a time. So in the first pass, you can see that 5 tokens are generated. In the first pass, in one pass, 5 tokens are generated. So Japan, then apostrophe S benchmark was accepted, but bond was rejected. Instead of bond, N was generated, right? In the second pass, let's say another 5, and then eventually in each of the pass, some number of tokens were accepted or some number of tokens were speculatively decoded, right? So in total, it has 37 tokens. Now, if you then have used speculative decoding, then it would have required 37 forward pass. But since we are using we are using speculative decoding, it just requires 9 forward pass, and that's a huge gain. So if you can think that the straightforward, like 4 times less number of this target model, the big model. Of course, we have to call the draft model. Yes, that's why the probably ultimate speed up will not be 4 times. But still, this is like significant. This will be a significant speed up. And again, that's why I'm saying, what about the forward passes through the draft model? That will also take time. So that's why we shouldn't be like very aggressively guessing. So this is the hyper parameter. How many tokens should we generate on the draft model before verifying it using the best model? So that's the hyper parameter. And remember, if we have if we guess like too many tokens, that will also waste some compute. Even if it's a draft model, still some compute is needed, right? We cannot say that the guess is happening magically or without any compute. So it's a hyperparameter. We shouldn't set the hyperparameter to a very high value. It usually comes from experimentation, like what should be the value of the hyperparameter. If we set it to a very high value, then it will result into like wasted compute on the draft model. Although small, it still waste the GPU time, right? Yeah, and then we can, the idea is we can have this C, which is compute ratio of the draft to base model. If we have low C, if the compute ratio or number of computation in the draft is less, that means we can have higher cases of tokens per round. Okay, so that means the draft model, the smaller model, is cheaper, right? If we have cheaper, smaller model, then we can have the number of cases as high. So that's how this speculative decoding works. Okay, so that's the end of the material I prepared. Thank you very much. So if you like this material, this is just a glimpse of a big course which I already floated in NPTEL. The course name is Computer System Optimization for Machine Learning, where there I covered many of these kind of topics. So I just showed you a small segment of topic on large language model, but in the course I actually covered many of such topics in convolutional neural network, then large language model, then graph algorithms. So if you're interested, you can scan this QR code and then enroll for the NPTEL course. And NPTEL courses are free for enrollment if you know. So yeah, thank you very much. Now we can have questions. If you have any questions, please speak up or put it in the chat. I think there was already a question. Let me first answer that question. So yeah, the question was, if you are starting our AI career today, what would you focus on learning first? Would you explain the hierarchy of areas to be learned? So this is a very tough question. I mean, to be frank, I also don't know the answer. So when you say starting our AI career, I mean, do you want to develop models or you just want to use a model? If you want to develop model, then the basics of AI is statistics. Okay, nothing but statistics. So you have to know, you have to have a strong base on like linear algebra, probability. Then you can understand like how AI actually works, right? That's how we do. I mean, we means I'm no expert in AI. We work on system side, but that's how the researchers in AI go with it. But if you just want to use AI and then build some tools on top of it, I don't know what is the starting. Okay, any other question? Yeah, so since there was not many questions, I finished early. But please go ahead and ask questions if you have any. Don't hesitate thinking that your question might be stupid. No question? Okay, looks like everybody had a very heavy lunch. Okay, fine. If there is no question, then yeah, thank you again. Thank you for listening. Can we expect our servum models to reach frontier level? I am not sure what is servum model. Maybe can you explain what is servum model? Yeah, I am not sure what is servum AI. I mean, see, I mean, whether it will reach frontier level or not, I am no one to comment there. I mean, it's totally the job of engineers to do that, but we have already seen what these AI models can do. Any model can be at that part, right? Any other question? Okay, fine. So again, if you have any question offline, you can always send me an email. With that, thank you very much.
Thank you, sir, for the enlightening and highly informative session. We sincerely appreciate the time and effort you have taken to share your expertise with us. We also thank all the participants for their active involvement and meaningful interaction throughout today's session. With this, we conclude day 1 of the Faculty Development Program. Thank you and have a wonderful day.
Thank you. Bye.